the pilot need about the fuel system? I'm confused on while answering these questions. I guess the fuel quantity is the first information that pilots should know.
Yeah.
Beside that, does any
generally you'll want to know the temperature of the fuel. If it kind of depends on the aircraft type, but most aircraft will have a fuel temperature, so he knows that his fuel's not getting too cold. He needs to know that he's got proper fuel feed. Yeah, so you've not got a fuel imbalance.
Okay.
And I can't remember the other one off the top of my head. I'll get back to you on that one.
And another thing, if the aircraft is equipped with more than one booster pump, and the aircraft is an MEL, I think that information also the maintenance team should immediately share with the pilot.
No, if you've got an unserviceable pump,
okay,
you need to look into the MEL to see if you're allowed to fly with an unserviceable pump. If it is, yes, then the crew would be informed. It'd be put into the ADF, I would imagine.
Yeah,
the ADD log.
Yeah,
the deferred faults.
Log. Yeah. Okay, thank you, Jim. And another query on indication that ice indication. The question number 30, I'm confused. What indication would the pilot have of ice detection system failure?
You get a warning light on the CWP.
Does it have the annunciator also? Or
no, it's just a light. You get a fail light.
Do we need to confine? Is it red or only light? Amber or?
Be amber.
Okay. Because as far we have covered the three type of ice detection system. In hot rod, there is no cockpit indication. And in serrated, as far as I have worked with some aircraft equipped with serrated ice detection system, there was no cockpit indication. And the vibration rod, I'm confused. I've worked, but I have not noticed about vibration. And out of three indication system we covered in our textbook, the two detection system, there is no cockpit indication at all. The hot rod and serrated.
Are you sure?
Yes. I'm just talking about based on my experience. I'm not talking about in general. I don't have much idea on overall aspects. I'm talking simply based on my experience.
Yeah, don't run on. Yes, experience is good, but you need to go with what's in the notes.
Yeah, in the note, I have not found anywhere mentioning the cockpit indication in case of failure of ice detection system. The note which has been provided by the AST. Yeah.
Just give me 2 ticks. What question number did you say? 30?
30, yes, sir.
Yeah, what indication would the pilot have of ice detection system failure? There would be a light comes on in the cockpit.
Okay.
Yeah.
In the question number 19.
Yeah. Go. You'd have to read it out to me. I haven't got them open in the front of me.
No, you have already opened. That's why I'm telling the same question number 19 in the ice that ice detection only. It's asking about the normal operating temperature of heated windscreen, and we have two temperatures, 40 and some 40 and 55 is there, I think.
Yeah.
So I got
What's the normal operating temperature?
because in it will come overheat, something is there. That's why
Yeah,
I
so
want to
the
confirm.
normal operating temperature is its everyday operating temperature. The second controller, if you get a failure in the first controller, the second one will take over, but it will control at a higher temperature. So the
Yeah.
normal operating temperature, I think it says in the notes, is about 40.
Yeah.
And then the higher temperature is 50,
55.
55.
Yeah, 55. It's 55. So we have to answer here 40, right?
Yeah, that's the normal temperature.
Okay.
Jim,
Thank you.
yeah,
Yep.
in connection with the same question, is it 40 or we can say the below 40?
No, it'll control at 40, won't it?
Okay, okay. Because once it is reaches the 40, the supply is cut.
No, it'll be maintained.
Okay, okay.
That windscreen is going to be heated right the
Oh,
way
yes,
through the
yes.
flight.
Yeah, maintain. Okay, okay. Thank you, Jim. I got. Yeah.
Anybody else? Okay, then we'll rattle on with the rest of hydraulics. We'll finish hydraulics this morning, and then we'll do pneumatics this afternoon.
Jim?
Tomorrow morning. Hello.
Yeah, one more in hydraulic only. We have some questions at the after the end of the chapter, and I want to ask which we already covered. There is two questions that is confusing me. That's why in the notes we have the same.
In hydraulics.
Yeah.
Yeah. Well, I didn't send any questions out, did I, for hydraulics?
No, no. In the notes you have provided, in that at the last there is some questions.
Yeah.
So in that we already covered. That's why I try to find the answers and I get confused.
Okay then. Which questions?
18 and 19.
Okay.
Yeah.
So question 18. What's the problem there?
So it's asking about the component that would provide the system pressure exceeding its maximum value during periods of service inactivity.
Yeah.
So that is ACOV.
Yep, that's it.
Okay, and one more 19 just below there. A component that would ensure the correct direction of flow of fluid, the correct side of an actuator piston. So it's a selector valve.
Yep.
Okay, then that's it.
Okay.
Yeah, thank you.
Jim. Jim.
Yes.
In the above question that in number 18,
Yep.
if there is an option, another option, poppet valve and ACOB.
No,
It happens.
the poppet valve is one of the little components in the ACOV.
Okay, not itself of valve.
The valve that's doing the work is the automatic cutout valve. The poppet is just a little valve inside that. The working parts.
Okay, Jim. Okay, got it.
Okay.
Thank you.
Hello, Jim.
Yep.
What about answer of 17 number question? Same as 18 or reverse? Hello.
Yeah. So if the ACOV is protecting the system when there's no load, when there's no services being operated, yeah. What other component that we're going to use to protect the system from overpressure?
Pressure reducing, pressure relief.
Pressure relief valve. Yep, that's it. Okay.
Yes, Jim.
Anybody else? Super duper. Right. As I was just saying, what we'll do, we'll finish hydraulics off this morning. We'll do pneumatics this afternoon. Then tomorrow morning we'll do fire protection, and tomorrow afternoon we'll maybe just have a run through all the subjects, a recap, and if anybody's got any questions, any problems with it, any bits we need to go over, pardon me, we can do that. We can have a look at that.
Okay, Jim.
Okay. Right. So the next little bit in our hydraulic adventure, should we say, is looking at the pipes that we put in the system. Dead easy. Look at the different types of seals that we're going to use, and what they classify as miscellaneous components, just the little odds and sods that we've got in there in the system. Can everybody see the presentation okay?
Yes, Jim.
Yeah, fantastic. So pipes then. Your pipes are categorized into two groups, rigid and flexible. Flexible pipes are known as hoses. Obviously, they're going to be inspected regularly. For all your pipes, if you need to change them, yeah, we can only identify them by part number. A lot of them slightly different materials, slightly different lengths. So if you're changing a pipe, just go by part number. International symbol for hydraulics is a black circle on a white background with a highlighter through it. Well, a black circle on the white background, but you're going to put the highlighter through that. Yeah. So remember, we looked at the international symbol for fuel, which was a white background and the black star. For hydraulics, it's the white background with a black circle on it. Very important you remember that one. Yeah. Sometimes, if you're really lucky, a bit like the fuel, there'll be another bit of tape with hydraulic written next to it, but it's the black circle that we're looking for. And sometimes, again, if you're lucky, if it hasn't come off, you might find coloured tape, blue and yellow background or white background with those letters on. Again, sometimes, not always, you might find on the pipeline a direction of flow arrow. So that sort of thing, that is the bit we're looking at to tell us that it's hydraulic. The black and the white, black circle on the white background. The yellow and blue tape with hydraulic written on it, again, you might well get that. You might get the direction of flow. And in some systems, or some aircraft, not all, they sometimes have a system code to identify which system that pipe's running through, or running through. So on the slide, it says hydraulic left gear. Yeah, it might well be that there's a code on the pipeline. Instead of telling us it's the left gear, that C2 will refer to a particular system, and we've just got to go to the manual and look it up. Your rigid pipes, yeah, the material they're made out of depends what pressure they've got in them. Old aircraft going to use tungsten, brass alloy. New aircraft, newer pipes, steel, stainless steel, pneumonics, titanium. Again, those materials are very, very light and very capable of dealing with high pressures. Low pressure side of things, you might well find that we've got aluminium alloy pipes. So the material depends on the pressure that we're whacking through them. Don't need to worry about pipe classification. Yeah. Just be aware, don't spend hours revising it because I think it's more module 7. But the different types of end fittings are flared ends, flarelet ends, and swaged couplings. The flare, yeah, just the pipe is flared out at the end. There's a support collar put on the back, and obviously your union nut. To mate it with another pipe, depending on the type of adapter, if you've got a union adapter, then we need to fit a nipple into the pipe, and that allows us to mate the two together. If you've got a coned adapter, one with a cone on the end, then we're sweet. Everything fine. So that's your nipple there. Flared fittings, yeah, need the support collar because the flaring operation weakens the material, can cause cracking, can cause leaking. Nipples we've talked about, flaring, yeah. Don't need worry about that, and we don't need worry about that. Flare-less couplings, yeah, we're not messing about with the pipe. We're just putting an artificial flare on the pipe and bonding that on, yeah, and that will mate up with your union adapter. Yeah, it says it's pressed onto the pipe. Yeah, it's compressed onto the pipe, but it doesn't deform anything. Yeah, and the slide itself just a little groove, and as we squeeze the pipe together, that little what they call a pilot will grip into the pipe itself, and that will form the bond between the two. Again, just be aware of them. Don't spend hours looking at them. Swaging. Swaging is where we're going to use a special tool, special high pressure tool, and we're going to squeeze the end fitting onto the pipe. Yeah, again, it's because it's a special tool, the pressure it applies very, very high, but it doesn't deform the pipe during the swaging process. Swage couplings tend to be very good. They tend to be fairly reliable, you know, so we're not having to replace them very often for leaks, unlike other pipes. And they say you can get quite a reduction in weight by using the swaging fittings. Fewer leaks, as we said, and the end fitting just squeezed onto the pipe. Your flexible pipes, flexible hoses will compensate for any vibration. Yeah, it'll allow for movement of our components. Some pipes, you can just change the end fittings. That tends to be on, I say tends to be, the time I've come across using reusable end fittings is on older aeroplanes. Normally, you just get the part number of the hose and order a new one, and it comes already assembled. You're not having to mess about changing end fittings. Yeah, it's just Teflon in a tube. Teflon resistant to the fluids that are going through, so they're not going to break down. And then a braiding around them, that can be either fabric or steel, just to protect the Teflon, protect the outer sheath of the pipe as well. And then depending on what region it's in, there might be another protective sleeve on the outside of the pipe. Yeah, again, just example of your end fittings, but don't waste time going over that. Don't go too deep. Just be aware that they exist. There are different types of end fitting. Your end fitting 90 degrees, straight on, 60 degrees, all the rest of it. These bits just squeezed in. You've got your external braid covering your Teflon inner, and then 9 times out of 10 you're going to get a protective outer coating on the hose. Again, don't worry about the classification of the thing. Yeah. Just remember, a lot of hoses, there's a yellow or a white line running down the length of them, and that's just an indication that when you fitted the hose, it's not twisted. Yeah, you're not getting an indication of twisting. Yeah, so that's the sort of thing you're looking at. Distance between the end fittings, yeah, just where they're measuring from the center of the nipples, basically. And again, just the makeup. As I say, don't worry too much about that. And I think that was it for our pipes. Don't think we've missed anything there. Yeah, the important thing to take away from that little lot is the identification of hydraulic pipes. The black circle on the white background. Okay, bingo. Right. Drain and sampling points. Within our hydraulic system, we're going to need to, at some point, drain the system out for whatever reason. And regularly, we are going to have to take samples from the hydraulic system. So within the power generation side of things, what we'll do is we'll fit sampling points, yeah, where we can plug in, take a sample of oil without having to drain the whole system down. And we'll also fit drain points so we can empty the system should it become necessary. Because you're draining it all out, yeah, the drain's going to be in the lowest part of the system. Yeah, your sampling points are going to be in the suction and the pressure lines. When it talks about suction lines, the suction line is from the reservoir to the pump. Yeah, watch that one because it's terminology, but in the exams, if you get a question on pumps and connections, which we'll look at in a bit, if it's talking about the suction line, that is the feed into the pump from the reservoir. The pressure line, obviously, the line going out of the pump. Your drain points, your sampling points tend to be, or certainly your sampling points, self-closing valves, yeah, little self-sealing couplings. So again, you're not having to drain the system out. And those self-sealing couplings, so the self-closing valve as it calls it there, have always got a pressure-tight blank fitted over the top of them, yeah, just in case of any leakage. Yeah, so your drain points, just normal access point. You'll take a pressure cap off. That will allow the system to drain out. The drain's at the lowest part. The sampling points in the suction and the pressure line for taking samples when it becomes necessary. Yeah, and a nice little picture of a man taking a sample there. Yeah, nice to see that he's left all his spanners lying around. Reservoir, reservoir, reservoir. Yeah, and your actuators that we talked about, there'll be accumulators in there somewhere, selectors, all the good stuff. We will at some point need to fit a hydraulic rig onto the aircraft so we can carry out functional checks, where instances where we need to leak check something, to operationally check something. So we need to plug into the system, be able to connect our hydraulic rig to the aircraft. And again, we're going to do that via self-sealing couplings. Quick release couplings, where the hose screws onto the fitting on the aircraft, and as the two halves of the coupling come together, they're going to open up and allow passage of oil from one side to the other. that's generally what they look like, and that's the pressure cap that we get on them. Yeah, within the self-sealing coupling, we've got, sorry about these little things coming up. We've got a valve in either side, and as we join the two sides together, a plunger opens the valve, and that gives passage for the oil through both of them. So that's pretty much how they work. Yeah, little valve on a spring with a wedge, another one fixed valve on a spring, and what we're going to do is screw the two halves together. One half, normally the male half on the hose, the female half on the aircraft side of things, and as we screw the male half onto the female half, the two valves come together, they force each other apart. So now we've got a clear passage for fluid through the connection into the aircraft. As we unscrew the valves, the spring loaded, they will revert back to their closed positions. So we're not going to get oil out of there. We're not going to get oil out of there. We can put the blanking cap on the aircraft side, put a dust cap on the female side, on the male side, the hose side, and that's us. Away we go. Everybody okay with that? Drain points, sampling points. Fantastic.
Okay,
Right, on to seals then. Yeah, seals are there to prevent leaks, obviously. There are two classifications of seal worth remembering. Yeah, we have static seals and we have dynamic seals. Static seals seal two items that have no relative movement to one another. Dynamic seals are for components that do move in relation to each other. So a static seal, yeah, you're going to say put a plug into a pipe or whatever it might be. Yeah, they're not going to move in relation to each other. So that seal will be classed as a dynamic seal. Sorry, a static seal. A dynamic seal is where you're going to have movement. So the sealing on a piston head, yeah, because the piston's moving in and out of the actuator body, that would be classed as a dynamic seal. Again, highlighter, highlighter, highlighter. This comes up regularly. Yeah, you've got to have the correct seal and the correct fluid combinations. Yeah, your caster-based fluids have natural rubber seals. Your mineral-based fluids have synthetic rubber seals, and your synthetic oils, your phosphate ester synthetic oils, have butyl, ethylene, propylene, or Teflon seals. Okay with that? Don't worry about the numbers on the slide, but caster is your natural oils, natural rubber. Mineral oils, synthetic rubber, synthetic oils, the four specialist material seals. Any seal before we fit it needs to be lubricated, and it's lubricated using the system oil. So if you've got a mineral oil system, you get a new seal, you're going to get a bit of that mineral oil and you're going to rub it around the seal just to lubricate it before you fit it. Different types of seal that we'll come across, the good old O-ring. Yeah. O-ring can be used as a static or a dynamic seal. In the static instance, yeah, it's just going to, as we tighten the banjo down in this case, yeah, it's just going to compress the seal, and that will form a seal for us. In the dynamic side, if we're using it, yeah, dynamically, above I think it's 1500 psi. It says in the notes above 1500. That is classified as high pressure. And if we're using a high pressure O-ring in a high pressure system, then it needs to have backup rings fitted. And again, that paragraph, stick a highlighter through it. Yeah. High pressure seals, anything above 1500 psi considered high pressure, then you've got to have backup rings. And the reason for that, it stops the seal being dragged backwards and forwards when the piston's operating or whatever. Yeah, so you got your pressure in there, the ram moving against the cylinder. Because you got pressure, as the ram moves, it can drag the seal, which in turn is just going to knacker it, and then you're going to end up with leaks. So what we do, we just put little Teflon backup rings either side of the O-ring, and that gives it the support it needs to do its job. Okay with that? Bonded seals, yeah, are a steel washer with a rubber seal bonded to the inside of it. Normally, in fact, normally they are static seals used for things like banjo bolts and what have you. Square section seals, yeah, again, just as the name suggests, they're just like O-rings, but they're square in section. Thing with square seals is they are a pain because they tend to roll. And once they've rolled, they're out of position and they'll leak. So just be very careful if you're fitting them. Duplex, made up of both soft and hard rubber, and they again give us a protection from low and high pressure. Different applications. I think it mentions accumulators for duplex seals, but the one side is soft, the other's hard. Yeah, your V-section seals. Again, they're a one-way seal, so if we need sealing in both directions, you've got to get two, fit them back to back. Little lips, sometimes they are reinforced with a spring down the inside. Other times they'll just be left as you see there, just the V-section seal. Again, the only thing to remember with these is if you're using them in two directions, you need two seals back to back. T-section seals are essentially your O-ring with the backup fitted to it. Yeah. So rather than having backup rings, we can just make up a T-section seal, and it's having exactly the same effect. Wiper rings aren't considered to be seals, but they are very important. We'll put them on areas where there are relative movement. Probably the best example would be an actuator. So where the piston and ram move in and out of the actuator, we'd fit a wiper ring, and that's just going to keep any crap outside of the actuator body. Yeah, so it's wiping the ram as it's extending and retracting, and it's making sure that any accumulated shit's kept outside, not getting dragged inside the actuator. And again, just examples of your different types of seal that you might come across. Actuator, we're going to have the wiper ring. We'll have a seal on the piston head. We'll have a seal on the rod or the ram if you prefer, just to prevent any leakage coming out of the actuator body. And again, just examples of the square section, the V section, duplex seal. Duplex seal with that reinforcing and that I was talking about. V seal with the reinforcing, sorry. Yeah, just a spring that gives it that extra bit of strength. Ta-da. Everybody okay with that? Any questions there? Oil coolers, yeah, we've said that with our hydraulic oil, as it's circulating, it's going to get warm. And we don't want it to get too hot. So what we do is, as part of its normal circuit, we can run that oil through a cooler or heat exchanger. Yeah, the heat exchanger is fitted where there's significant flow of the oil where it's going to get warmed through. And all we're going to do is pop it through some form of heat exchange to take that heat away from the oil. It can be just like a radiator. We can use ram air. Yeah, run the hot oil through the radiator one way, ram air cooling the other way, and that'll cool your oil down. Or what other method we can use is to run the pipework through the fuel tank. Yeah, so that cold fuel in the fuel tank, taking away the heat from the oil, the fuel's going to warm up slightly, the oil's going to cool down, absolutely belting. Best of all worlds. Yeah, so you pipe in. Yeah, and it's just a series of coils that live in the fuel tank, on the base of the fuel tank, and then as your oil's cooled out, away it goes. Top tip, yeah, it's not part of your exam, but if you get an aircraft where you are losing hydraulic fluid, the hydraulic level's going down, and you can't find any trace of a leak anywhere, drain a bit of fuel out the fuel tank and see what colour it is. If your fuel's turned pink, it's a good indication that your cooler's leaking. Yeah, can save you weeks of work just by draining a bit of fuel off. They don't leak very often, but if they do, obviously all your oil's just getting mixed up with the fuel. You won't notice it because it gets burnt with the fuel while the engines are operating. But it's worth noting if you lose your hydraulic oil. The other type of cooler we get is just a straightforward oil in through a series of pipes, comes out, and the other direction we're gonna let ram air across, cooling air that's going to blow across the heat exchanger and take away any heat from that circulating oil. Has anybody got any questions on any of that little lot?
Excuse me, sir. In this hydraulic system, where we use these coolers, but this hydraulic will not produce that much of heat on the system.
Say that again, sorry.
As practical, we didn't have seen till yet that hydraulic system needs cooler.
Yeah, as it said in the notes there, it's anywhere where you've got a significant flow. Yeah, so if the pump's churning around all the time, the oil's flowing around the system, it's not got any demand on it. It's going to warm up. Yeah, and all putting it through the cooler just means we're not allowing it to heat up too much. Yeah.
Okay.
Okay. Right. Quick look at emergency systems then. Yeah. Hydraulic systems. There's always going to be room for failure in a hydraulic system. Yeah. And if we do get a failure in the main system, we need to provide some sort of backup, some sort of reversion. Oh, I know what I meant to say to you guys. Congratulations. I saw in the news yesterday that the Nepali mountaineers are the first people ever to climb K2 in the winter.
Yeah, 10 people.
Team of Nepal.
Yeah.
Thank you.
7 summit, guys.
7. That was fantastic. Fantastic achievement. I just saw it in the news yesterday, so. Right, so that's got nothing to do with emergency hydraulic power, but I thought I'd just say congratulations. Your emergency, eh? Yeah.
Yes,
Your
thank you.
emergency systems are separate from the main system and generally have their own components. They will plug into the various systems at some point, but the emergency system is separate to the main system, has its own components. Yeah. Your normal power is supplied by engine-driven pumps. So normally each engine will have a pump on it. Those pumps will be running. If you get a failure in one engine, then the other engine will carry on. You've still got your normal feed. If we get a failure for whatever reason in the main system, we'll have our backup in the form of an emergency pump, and the emergency pumps are normally electric. The electric pumps, alternating current motor pump is what ACMP stands for. Driven from the electrics, AC as it says, and they're fitted on little vibration fittings, so the pump isn't going to suffer unduly from vibration in the aircraft. Just a little electric motor, driving a hydraulic pump, and we will select that in the unlikely event of an emergency. There's a little bit about helicopters. Because we're talking generic systems, the systems we're talking about marry up to fixed wing and rotary wing, and the rotary wing guys get very, very upset if you don't include them. So we bunged a helicopter in there as a good example. The AW109 fitted with 2 independent flight control systems, each system capable of operating the main blade actuators. So if you get a failure in one, you're not losing the aircraft. The thing's going to carry on running. The utility system, 2 accumulators, a normal accumulator, and then the second accumulator there is there in the case of an emergency, limited to operating the rotor brake, the wheel brakes, and the nose wheel steering, nose centering. So again, just examples of the types of component we'll get in emergency system. Your fixed wing, again, this is just an example, but what we've got is 2 main systems, a green and a yellow. The green and the yellow feeding various components. You'll notice it's the primary flying controls that they're feeding. If you get a failure in the green system, the yellow system is there as backup. If you get a failure in the yellow system, the green system's there as backup. Green and the yellows operating their own individual components as well. So that the elevators, one system's running the elevators, the other system's running the elevators. No mix and match. And then you'll see again for all your primary controls, you've got that emergency electrical backup. So you could have 4 or 5 hydraulic systems depending on the aircraft type and the size of the aircraft. Another method is the air turbine gearbox, where we take engine air, or APU air, and we can get that to run a gearbox, and on that gearbox there's a hydraulic pump. It says we can use that during ground maintenance if we've got them, and it's a 3-position switch, on, off, and auto. Normally these things would be selected to auto. If we had a failure of the hydraulic system in flight, then the turbine gearbox would come online, and it would start driving our emergency system. With the gearbox, we'll check it for overspeed. What you've got is a controller, the controller monitoring what's going on, looking for any faults in the main system. If we get a main system failure, the controller will open up the pneumatic system. Pneumatic system will run the turbine from the gearbox. As that turbine is turning, it's turning the gearbox, and at the same time, the gearbox is turning a hydraulic pump. Easy as that. Yeah, we don't need to go any deeper than that. Just know that the bleed air driving a turbine attached to the gearbox will have a hydraulic pump attached to it. Something we discussed last week was power transfer units. And the PTUs are essentially two pumps mounted back to back. One of them will act as a hydraulic motor, the other will act as a pump. Yeah, so if I get a failure in one system, I can select the power transfer unit. The good system will act as a motor, and it will drive the other one to act as a pump to give emergency hydraulics. The thing to remember about PTUs, and again, it's in the paragraph, the two halves of the power transfer unit are connected mechanically. So there's no mixing of fluids within the power transfer unit. So if you've got a leak on one side, yeah, and you run the PTU, you're not going to lose all your fluid from the good side into the other. So because that mechanical link, there's no mixing of fluids. Some, not all, may be reversible. Yeah, so they can swap systems, but that doesn't apply to all, only some. And that's we discussed this last week. Yeah, you've got a pump running, pistons going in and out, driving your swash plate. Yeah, and as the swash plate drives, there's a mechanical link, yeah, a shaft between the two. As this one's rotating, it's rotating the other one. Pistons working in and out, and in this case, they're acting as a pump for the duff side. Yeah. Again, just examples. That's your spline shaft. This one could be a pump, could be a motor, whichever way around we're going to use it. Spline shaft, and the two connect together. And because of that spline shaft, there is no mixing of fluids whatsoever. So you're not draining off the good side into the bad side. The RAT, the ram air turbine, fitted to a lot of aircraft, and the ram air turbine is just a little propeller, yeah, that will stick up into the airflow, and as the propeller rotates, it's going to drive a little gearbox with a pump on the end of it. Yeah, the RAT self-contained unit. This one shows it popping out the upper fuselage. All the ones I've come across drop out from the bottom. Yeah, so it's so basically it's just a propeller that's connected to a hydraulic pump. Normally it will be in the closed, in the stowed or the locked position. If we get an emergency, it will either deploy automatically or the pilot will select it. Again, generally there'll be an automatic selection. The system monitoring pressure. Get a failure in the system, the thing will drop down into the airflow, and the propeller will start rotating. Yeah, as it rotates, it's bringing the pump online. It's going to start pumping hydraulic fluid. As I say, it's manually switched, or it can be automatic. To make sure that we get a constant speed on the propeller, it's a variable pitch propeller. So it doesn't matter what altitude or what attitude the aircraft is, that propeller is variable. Yeah, so we're ensuring that we're getting constant speed. and that's just done by little weights that are built in within the operating head. The other thing we have is what they call a volumetric fuse, and the volumetric fuse is there to stop the pump coming online until the propeller is up to running speed. So the volumetric fuse will stop the thing from, or stop the pump coming online. I think it's for about 5 seconds. I'll double check my figure. But it holds it off for a few seconds. That means the propeller's up to speed, and now we can put a load on it. Please whack your highlighters through the variable pitch, which is giving the propeller constant speed at altitude and attitude, and the volumetric fuse, which prevents the pump from running before the propeller is up to speed. Whack your highlighters through those, please. Yeah, again, just examples of the RAT. Deploys from the low surface of the aircraft. In this case, all the ones I've seen do. Yeah, just pops out into the airflow, normally automatic. Variable pitch propeller and the volumetric fuse. Once it's up to speed, it's turning that hydraulic pump, it's generating hydraulic power. Yeah, and again, another example. Yeah, your little weights in the operating head just make sure that the blades achieve the right pitch. Anything I need to say about those? No, they get functionally tested every so often. If they are being tested, you've got to put follow the manual, follow the AMM. There's a special safety cage should fit over it in case anything goes wrong. And if you do get involved in functionally checking these things, make sure you've got ear protection because they are bloody loud. Yeah, as they run up to speed, they're really, really noisy. Other emergency facilities we're going to get, we've talked about these before, accumulators. And the accumulator is going to store your fluid under pressure. So if we do get a drop, then that compressed gas in the accumulator is giving us a head of pressure that we can use. Obviously, the size of the accumulator depends on what we're trying to achieve. If you've got an accumulator for the wheel brakes, for example, it's going to be reasonably large because we're going to need sort of 8-10 applications of the brakes to bring the aircraft down to a halt. Something like the landing gear, yeah, you might need a smaller accumulator because all you're trying to do is open the doors and unlock the gear. Gravity should do the rest. So again, the size of the accumulator depending on the service that we're going to operate from it. Yeah, normally one shot, you get one go at it. As I said, brakes are slightly different, but normally it's just one go. Something like lowering the landing gear, you pull the emergency handle, the accumulator should have enough pressure just to unlock everything. And if you're down to using the accumulator, we're down to pretty much the last resort. Yeah, we've not got anything left in our armory. Instruments that we're going to use on our hydraulic system. What do we need to know about? We need to know pressure. Yeah, we need to know quantity, and we need to know temperature. Somebody after me there?
Yeah.
Yeah, go on.
We have accumulator for emergency. We have separate accumulator or only one?
Normally a separate one.
For the emergency backup system?
Yes.
Okay. And if there is air leak in the accumulator, in this emergency accumulator, so it will not work, or what will happen?
It won't work. If you haven't got any air pressure in it.
No, I'm asking if it is leaking or low air than in the low air pressure in the accumulator, the backup accumulator.
That sounds like you're reading a question off a sheet there. Go on then. You answer the question. What do you think will happen if you've got low air pressure?
So that will not work. I don't know. I don't see the question. Simply I'm asking.
Yeah, no, you're right. If you've got low pressure in there, it's either not going to work or it's going to be very, very sluggish if it does. Very, very slow.
Okay. Okay, thanks. Yeah.
Anybody else before I move on? No. Okay, right. We'll just finish this bit and then we'll have a cup of tea. So what we're looking at is, for our instrumentation, we want quantity, pressure, temperature. Yeah. Again, stick your highlighter through those three aspects. Yeah, we need quantity, we need pressure, we need temperature. Yeah. Those indications are normally repeated for the emergency side of things. It can be on a combined gauge. Yeah, but we're always going to have a quantity indication, we're going to have a pressure indication, we're going to have a temperature indication, and if we see anything unusual there, we know we've got a problem in the system. Yeah, indication. Yeah, as we're looking at indication, we're monitoring the system. If we get a warning, that's telling us we've got a failure within the system. Difference between the two. Yeah. Quantity telling us how much we've got. Yeah. Quantity we'll have at the reservoir. Yeah. The reservoir will have some sort of sender unit, be it a float switch, be it transmitter, whatever, and that information will be repeated up on the flight deck, so we can see what quantity we've got. In our hydraulic system, yeah, so it's showing you your engine oils there, your hydraulic system, left reservoir, yeah, right reservoir, and obviously if we look at the two reservoirs there, they're different capacities, they're both showing up as full. Yeah, your float switch, as I say, some sort of rheostat, repeated indications, one for the ground servicing panel, one for the flight deck. If the quantity gets low, then that's going to put on a low level warning in the cabin. Temperature, again, we're going to monitor the temperature of the oil, and what we do is just put heat sensors on the reservoirs, so it's monitoring the temperature of the oil that's coming back from the system. We can put temperature sensors on the hydraulic motors, on the electric motors. Yeah, and again, if we get the oil coming back at too high a temperature, we'll put on an overheat warning again in the cabin. Sensors, bimetallic strips, resistive bulbs, thermostats, don't worry about that. Just know that we've got quantity, temperature, and pressure. Yeah, your pressure gauges, direct reading or electrically operated, and all they're going to do is just tell us what the pressure is in the system. Pressure switches fitted in the system, they're going to be monitoring the pressure that's operating at. If we do get a failure, if we do get a low pressure, again we're going to get a warning lamp in the cabin. The crew can have a look and see what they're doing about it. Other indications, we might get accumulator indications telling us what pressures we've got in our accumulators. The isolation cock that we talked about before, we might have a light to tell us what position that's in. Don't forget, these are possible other indications. You won't necessarily have them. Reservoir pressure status. We said that the reservoir needs to be pressurized for the various reasons. And generally, if your PTU is operating, you'll get a light to tell you that it's online. Likewise with your RAT, your ram air turbine, if that is deployed, you'll get a light. Don't forget, these are emergency, the PTU and the RAT. In the event of an emergency, the pilot's going to be fairly busy. So by giving him an indication, he's just got the confidence. He doesn't have to worry about those elements of the system. PTUs, again, just an example of the power transfer unit, just allowing hydraulic power to transfer from one system to another. Yeah, so if you get a failure in the blue system here, yeah, the PTU, we can operate that, and that will drive the PTU on the other side as a pump for whatever systems it might feed into, in this case the landing gear. Yeah, just again, examples of gauges that come from the notes. And again, you can see there with your temperature, yeah, 50, 47, roundabout average. And then in this one, you've got a rocketing in the temperature. That would give you a heads up that there's something wrong within the system. Yeah, don't need to worry about that. Right, I'll just do this bit. It'll take 5 minutes and then we'll have a cup of tea, okay? 3 types of hydraulic system that we will come across. There is the self-idling system, the non-self-idling system, and the variable volume system. The self-idling system is where the pump will offload itself and circulate the oil back to return when there is no demand on the system. The non-self-idling system is the one that has the automatic cutout valve in it. The ACOV is going to give us that idling facility. Yeah, so the self-idling pump has it built in. The non-self-idling pump, we've got the ACOV in there, and the variable volume, we talked about that before with the adjustable swash plate. Yeah, so those are the 3 types of system. Again, make a note of that, please. The self-idling system allows the engine-driven pump to offload excess flow without the need for separate valves. The way we can identify a self-idling pump is that it has 3 connections. Highlighter. Self-idling, 3 connections. The suction that pulls in fluid from the reservoir, the bypass that returns the excess when we're not using any, when there's no demand on the service, and the pressure is the output from the pump. Yeah, so you're self-idling. Yeah, you've got the 3 connections. Yeah, you've got your suction line into the pump. You've got the bypass line back from the pump, and you've got the pressure line out from the pump. So if there's no demand on the system, the pump is just going to open internally and return your fluid. The non-self-idling, yeah, has not got that internal offload. We need the external valve, the ACOV. So your non-self-idling pump is identified by the fact that it's only got 2 connections, the suction and the pressure. And as I say, used in conjunction with the ACOV, highlighting, non-self-idling, 2 connections, ACOV fitted. Yeah, so there's your pump. You've got your suction, the line from the reservoir, your pressure, your line out. Yeah, and in there, your ACOV. So if if there's no demand on the system, yeah, any excess pressure that's building up is just going to get fed back to return. Demand on the system, then the fluid will go off to where it needs to be. And again, if you've got the ACOV in the system, you need the accumulator. The two have got to go hand in hand. Variable volume system. Yeah, we've got the pressurized reservoir, the variable volume pump, and all these components for the variable volume system tend to be held together in a module. Yeah, so your filters, your rig connections, all that sort of thing tend to be put into a module, and a module is easy to change. It's meant to make life easier for us. Yeah, so again, reservoir down to the pump, that variable volume pump. Yeah, and again, feeding into the module where you got your filters and all the other little components, and off to wherever it needs to be. This one, yeah, again, as the fluid isn't being used, yeah, it can get ducted off to a cooler before it returns. We've got filters in the system. It's all very nice and Gucci. Yeah, just again, example of a module. Your pressure transmitters on there. You'll have your filters on there. Your filter indicators. All in one unit. It says it makes fault diagnosis easier because all you're doing is changing one lump. You don't have to work out which components unserviceable. Personally, I think it takes away some of your skill level, but that's the way things are going. We just need one component, replace that, and that's the system back up and running. We don't need worry about that. Anybody got any questions there so far?
Jim.
Yeah.
Hello.
Hello.
Hello, Jim. Can you please explain the schematic diagrams of self-idling, non-self-idling, and variable volume again?
Yeah. I'll tell you what. We'll have a cup of tea first, should we?
Okay. Why not?
I'll do that.
Thank you.
But while you're going for tea, yeah, I'll do that for you. Right, in my book, it's page 111. I'm not sure what it is in your book, but chapter 9, typical hydraulic power systems. Yeah. Through to the end, which I've got as page 131. It might be slightly different in your books. The last figure. Sorry?
106.
106, right, up to it'll be about 124 then. It should be a picture of a hand pump system. Yeah, for a helicopter. Anyhow, up to the start of chapter 10. So all of chapter 9, we're going to skip. We don't need any of that. So you can fold that away. Yeah, if you've got hard copy, just bend it out of the way. If you're working on PDF on your laptop, don't worry about it. Okay. Right, I make that 10:30, so 10:50 my time, 20 minutes. Kathmandu, 16, 18, 20, so 16:40 your time.
Excuse me, Jim.
Yeah.
It's typical hydraulic power system we don't need.
No.
Okay then. Thank you.
Okay, Jim. Then have a cup of tea.
Okay, 20 minutes.
Thank you. See you.
Right, guys, got everybody back?
Yeah.
Yeah. Lovely jubbly. Right, I was asked to go back through the 3 different types of hydraulic system. Yeah, the 3 types we have: the self-idling system, the non-self-idling system, and the variable volume system. Yeah, that's what we need to worry about. The self-idling system has the ability to offload the excess flow in itself. Yeah, so there's an offload within the pump. So when there's no demand on the system, additional pressure builds up. Pardon me, we need that to offload. So the way we can identify a self-idling pump is it has 3 connections. It has the suction connection, it has the pressure connection, and it has the bypass connection. Yeah, so from your reservoir, your self-idling system has got the suction, which is going into the pump. It's got the pressure coming out of the pump, and it has also got the 3rd connection, the bypass. Yeah, so as system pressure builds up, yeah, the pump will offload itself and it will divert the extra excess back to the reservoir. Are you okay with that?
Okay, Jim.
Okay.
Okay.
The non-self-idling does not have that internal offload. Yeah. Because of that, we need to put a relief system somewhere else in, and we're going to do that using the ACOV. So with your non-self-idling system, the pump only has 2 connections. Has the suction from the reservoir, and it has the pressure off to feed the systems. Yeah. So for that system, we need an ACOV in it, the non-self-idling. Yeah. So from your reservoir, the suction connection, and the only other outlet from the pump is the pressure.
Okay.
Yeah.
Okay.
We've got the ACOV in there, so as pressure starts building up, the ACOV will just allow that excess to go back to return. What we do need, though, and as we've hammered home, is the accumulator fitted in conjunction with the ACOV. Happy with that?
Okay, Jim. Thank you.
Excellent.
And
the variable volume pump, that's its own story. Yeah, the pump, it's got the suction line in, it's got an offload capacity because the swash plate moves, and all the other components tend to live in a valve pack, a module. Yeah, so if we get a problem, we can just change the module. We don't have to diagnose. We don't have to fanny about. Yeah, we just change that.
Jim, it has also, the pump also have, as it is a complete module, but the pump also has 3 connections here in the schematic diagram.
Yes. Yeah, the variable volume, it's Like you say, you go from your reservoir down to your pump. Yeah, from the pump,
Okay.
you've got your case drain. Yeah, case drain filter via there. That's going to lead you through your cooler. Yeah, and that's going to go back up. So any offload is going to go back to return. The pressure line is going out through the module. Yeah, so that effectively is as a self-idling coupling, but because it's variable volume, yeah, it goes back. It's out through the case drain.
Okay, Jim. Okay.
In this one, okay with that?
Okay.
Right. Just for our emergency system, typical hydraulic systems. Yeah, we've got the red system, the yellow system, the green system, and all of them interconnected. Yeah, so if we get a failure, let's say we're failure in the green system, that's looking after primary flying controls. The yellow system is also looking after those flying controls. If we get a failure in the yellow system, the red system is looking after them, and some of the important ones the green system will look after. Power transfer units, yeah, I've got those as well. One running as a pump, one as a motor. Yeah, I've got a reversible one fitted in this system. And again, the green and the yellow system interconnected by transfer pumps. We've got the engine-driven pumps from both systems. You can see the engine-driven pumps. We've got the reservoir. And in here as well, we're going to have additional pumps. Yeah, so even more backup in the case of an emergency. Yeah, typical systems, all cross-connected, all interconnected. So in the event of failure of one, then the other will take over. Everybody okay with that?
Mr. Jim,
Yeah.
as you said that ACOB is a non-idling, yeah? Non-self-idling.
A non-self-idling pump will have two connections.
Yeah, it's suction and pressure.
Yeah.
ACOB is a non-self-idling, yeah?
Yeah.
Then we have already did the ACOB is a self-idling also, yeah? There's idling fluid.
No, the self-idling system, it's all done internally within the pump. There's relief valves in the pump. So we don't need an ACOV with that.
Okay.
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 Anybody else?
Okay.
Right. So this next little bit then, the chapter 9, I think it was, typical hydraulic power. We don't need any of that.
Jim, there is a few paragraphs here. I can see
There's a whole chapter.
that is glass cockpit displays and maintenance panel. These are also not required.
No, you need that. You need to know what your indications are, aren't you?
Yeah.
So what I said was chapter 9.
Yeah.
Yeah. Typical hydraulic power systems. And it goes through a 737. And it goes on to a TriStar. Then it goes on to, I think it's a BA 146. Then it goes on to helicopter hydraulic system. And eventually you'll come to the end of the chapter. And the last thing in there should be a figure showing you the hand pump system from a helicopter. All of that chapter you can skip. You don't need it.
Jim,
Yeah.
in helicopter hydraulic system, there is a tandem ram type. So can you please tell us only the tandem ram? What is the type?
It's two actuators in one body.
Okay, in the tandem ram.
Yeah.
Because I work in helicopter.
Yeah, it's just an example. Yeah, so what you get is one body, two separate hydraulic systems working in the one actuator. Yeah, so if you get a failure in one system, the other one will take over. Yeah. You actually cover. I'm just trying to remember. I'm pretty sure we cover all of this when we do the flight controls. Yeah, because it's all part of your.
But we are not going to do the flight controls. We don't in 12 B1.
Yes, you do. You do helicopter flight controls.
Okay.
Mr. Jim,
Yeah.
it's not necessary that modular valve assemblies.
Sorry?
Modular valve assemblies is not necessary.
Is what not necessary?
It's not necessary to do study or not. What?
Chapter 9. Yeah.
Yeah.
You
Modular
do
valve.
not need. For what we are doing, you do not need Chapter 9. It is showing you typical hydraulic systems from different aircraft, and that's type specific.
No, Jim, there is in chapter 8, there is two sections, modular valve assembly and symbols for hydraulic system diagrams.
And section 3.
These I think we have not covered.
Oh, the symbols.
Modular valve assembly
the symbols
and
for hydraulic components.
yes. And also there is cockpit, glass cockpit displays and maintenance panel. These also we have not covered. Which is itself in chapter 8, chapter 7.
We did chapter actually. What are we? We were looking at indications, weren't we?
Yes.
Yeah. So not every aircraft has got a glass cockpit, has it?
Yes.
Some aircraft have got analog gauges, some have got digital, some are really Gucci. Yeah. So all we're talking about is what indication do we need? It doesn't matter how it's displayed. Yeah.
Okay.
Yeah. So we're just saying that we need indication of temperature, pressure, and quantity.
Temperature,
yeah,
pressure,
so all
and
they
quantity.
are different examples. So on this one, hydraulic pressure. Yeah. This one showing you that your power transfer unit's running. This one showing that your standby system's in operation. This one, it's just a different layout, but it's giving you the same information: temperature, quantity, pressure. For your different systems. And your glass cockpit, exactly the same. It's telling you what your quantity, your pressure, your temperature are. They're just examples of the types of display you'll get. Types of indication. Yeah?
Okay, Jim. Okay, no problem.
That's all right. Anyone else? Anybody else at all? Right, so we don't need that. 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 Don't need that. Don't need that. Don't need that. That's what it's talking about with your actuators. Yeah, you're running two systems into the actuator. Yeah, so the actuator is duplicated internally. Again, we'll look at those later. If you remind me at the end of the lesson this morning, I'll dig out a picture of one, so just to give you an idea. Yeah, but remind me before we stop for lunch. Okay with that?
Okay.
Yeah, whoever it was that asked me about helicopters, yeah, just remind me.
Okay, sir.
Right, where I get to now. Ta-da! Right, system maintenance then, that we need to carry out certain maintenance on our system. Yeah, and whatever we're doing within the reaches of a hydraulic system, we need to make sure that we take every step that we can to prevent contamination of the system. So any area that we're working in, any area that we break into a hydraulic system, any work we do, we need to make sure that everything is nice and clean. Yeah, good clean working area. Again, for your system maintenance, one of the really important things is you're dealing with high pressure fluid, and that can do you a lot of damage if you're not careful. So we need to follow the procedures in the AMM to make sure that we stay safe, and that the aircraft is kept safe as well. Yeah. So follow the AMM precautions. If you don't, damage to both you and the aircraft will result. The high pressures in the system, if you don't follow the precautions, and if you break into a system that's not been depressurized, or the accumulator's not been relieved of its pressure, you're going to get a lot of high pressure oil coming straight at you. And if you get that in your eyes, yeah, you're going to be screeching. Yeah, so make sure you follow the precautions. Make sure that your system is depressurized before you do any work on it. It says get type training, know the aircraft system. Yes, but again, you're not going to get type training straight away. So make sure that the AMM is followed, the procedure. Stay safe. Keeping contamination out of the system. Yeah, we're looking at solid particles. They can be introduced externally, yeah, by not keeping things clean and tidy. But you can also get a lot of contamination in the system from components wearing. As I say, the pumps are notorious for breaking down. Yeah, and that, as it breaks down, you're going to get all these particles contaminating the system. Hopefully your filters will catch it and give you an indication, but we need to make sure that we don't allow that to go too far. One of the major sources of contamination is putting the incorrect fluid in the oil. Incorrect fluid in the system, sorry. Yeah, so what we said before about making sure that we put the correct oil in the system, again, reiterating that, and again, making sure that you use the correct seals with the correct fluid. Otherwise, that's going to introduce leaks and problems with the system. Overheating is another fault we can get. Yeah. If a filter becomes blocked, the oil's got to work harder. As the oil works harder, it overheats. And if the oil does overheat, it can start breaking down chemically. And once it starts breaking down chemically, again, that's going to lead to all sorts of problems within the system. So monitoring the oil temperatures, making sure your filters are clear, that there's no blockage in the system caused by contamination. Again, all critical to the safe operation. An incorrect handling of your equipment, throwing things on the ground, dents, damage, again, not putting blanking caps on, has all got the potential to introduce contamination into the system. If we do get contamination, we need to be monitoring for it. We need to be checking every so often. The prime source is your filters. Monitoring the filters, checking the popper indicators when we're told to do so, replacing the elements every so often. They get removed and replaced, and the old ones sent off for disposal or cleaning. A lot of these filter elements, the metal ones, can get cleaned. The other method we can use for checking the system is by using magnetic chips. And all they are little magnets on a stem, screwed into the pipelines at different points. And as oil flows past, if there's any particles in there, they'll be attracted to the magnet. Every so often, we take the chip detector out, we have a look at it, see if there's any debris build-up. If there is, we can send that off to get analysed. The labs that we use now are what we used to call EFDC, Early Failure Detection Centre. They'd analyse the debris that they found on chips and on filters, and they would be able to tell you which component was starting to break down. They're very, very good. You can get analysis done on the oil, what they call soap analysis. And again, that's going to show even minute bits of contamination. And even with that minute contamination, again, they can say, right, well, your pump's breaking down, or you've got a problem with this, whatever it might be. How can we prevent it? Blanking, using the correct blanks on our system, making sure everything's kept clean, that the equipment that we're using, the topping up equipment, make sure that that's stored in a clean environment. Make sure that your oil is stored in a clean environment. Lubricating your seals before we fit them. If you lubricate the seals, it helps you fit them, and it also makes sure that any crap is wiped off. Using the correct equipment, obviously, putting the right oil in the right system. We've talked about that. And part use cans of oil. Again, that kind of comes down to your operating procedures. Some companies, we used to call them Risbridges. And the Risbridge is just basically a hand pump that screws onto the oil can. You'd screw this thing onto your oil can, you'd top your system up, and the Risbridge would stay with that oil can until the oil can was empty, and then you'd replace it. Other companies, once you've opened a can of oil, you've topped up your system, they will say any oil that's left over, dispose of it. So part use cans, if you do use that system where you've got any oils left, dispose of it correctly. Don't just tip it down the drain. It's not good for the environment. And a lot of countries now are getting really shirty about the environmental side of things, and there's big penalties if you found polluting. So just follow the procedures for wherever it is you're working to get rid of any oil that needs disposing of. Follow the correct servicing procedures. We've talked about that, making sure that we follow those procedures. And filter blockages. Again, we're preventing contamination. If we've got an indication, then we need to to get onto it, investigate it, find out why. Yeah, liquid contamination, again, making sure we put the right oil in the right system, storage. If we get fluid overheating, yeah, make sure we investigate that. So any oil that's breaking down chemically isn't going to contaminate the system. If we've had a component out and we've cleaned it off, if you use solvents for cleaning, just make sure that they've been dried off properly and all traces of the solvent's gone, because the solvent can damage the seals. Yeah, and again, solvent in there, that's going to lead to contamination. Every so often, we're going to take samples. Yeah, and those samples will be able to tell us whether the system is contaminated or not. Normally, they're done on a regular basis. We used to do them, I think it was every 10 flights or something like that. Can't remember offhand. But what they do, the aircraft would taxi in. Within 20 minutes of the engine shutting down, we'd take the sample, do the test that you're meant to do, and make sure that the thing's not contaminated. The test that it talks about in the notes is what they call the patch test. Yeah, the patch test is worth remembering. Basically, what we're going to do is within 20 minutes of the engine shutting down, we're going to take a sample of oil, and as we take the sample of oil, we're running that sample of oil through a sort of filter gauze. As the oil goes through the filter gauze, it stains it, and depending on the degree of staining, how dark the filter goes, depends on the level of contamination we've got in the oil system. Once it's gone beyond a certain shade, then we need to, we've confirmed contamination, need to follow the procedures, but generally that's going to be draining the system out, flushing the system through, and replacing the oil. That in itself is a horrible, horrible job. Yeah. But this is your patch test. Yeah. Little connector that we put onto the aeroplane. We've got a sample bottle. Within the sample bottle, we've got like a little holder for these filter pads. Yeah, so we'll put a filter pad in the holder. We'll put a holder over a suitable container. We'll take our sample of oil and we pour the oil through the filter. Yeah, these bits here you can connect directly to the aeroplane and take your samples that way. Yeah, put your oil through, and depending on the degree of staining, yeah, the shade of staining depends on how contaminated we are. We have a little colour chart. We just slide the gauze behind the colour chart and just compare them. Yeah, so if it's normal, we'll have a look. Yeah, fine. A little bit heavier staining. Yeah, it's out with what we'd normally expect. Can we live with it? Do we need to check? And what they might say is, right, rather than check every 10 flights, they might say check every 5 flights. Yeah, if we get down to this level, really heavy staining, then we're in a whole world of pain. Yeah, if we think we've got contamination, obviously we'll go up the food chain, report it, see what the manual says. Could well say drain the system. Yeah, so if we've got suspect confirmed contamination, drain the system right down. Then we've got to replace the filter elements. Yeah, refill the system and operate all the subsystems, your flying controls, your landing gear, all the other bits and bobs. Operate them all through. Then drain all the fluid out again. Replace the filters, so the elements. Refill it again. Operate all the systems. Resample the fluid. It is a complete chew doing a system flush and check. And then depending on the manual, you might need to replace all the filters, the seals in the system as well. So, you know, keeping the system clean is saving us an awful lot of work. Yeah, so that's flushing the system through. Yeah, once we've done that, we're happy. We're going to fill the system to the correct level, making sure we use the correct equipment and the correct fluid. Yeah, all that is done in accordance with the AMM. And because we've been breaking into the system, there's a possibility of introducing air. Because there's a possibility of introducing air, what we need to do is to vent the system. And venting the system just means operating all the different services, and any air that's trapped should be pushed back to the reservoir, and then it can be thrown off to atmosphere via a vent valve in the reservoir. If we can't do that, if venting doesn't work, then we need to bleed the system. And bleeding is opening little valves at various points in the system and relieving trapped air via the bleed valves. Bleed valves normally located at upper parts of the system because the air is going to try and rise. But again, the AMM will tell you where your bleed valves are fitted. Yeah, before we do anything on the system, we need to make sure that all the pressure has been dissipated. Yeah, so making sure that the services have been operated, and if we've got an accumulator fitted in that system, either operate it 4 or 5 times to take the accumulator down to base pressure, or some accumulators have got a little button adjacent to them. You press that button and that will relieve all the pressure from the accumulator. Yeah, so making sure that all the pressure has been dissipated out. Yeah, changing components. Make sure that all the pipelines, open pipelines, are blanked. We get pressure blanks. Pressure blanks mean that we can operate the system with a component removed. Yeah, if it's not going to interfere. So if I've removed a brake unit, for example, I can put pressure blanks on the brake pipes and still operate the flaps or whatever it might be. Yeah, so if you're not going to be operating any systems, then just little plastic or aluminium alloy dust caps will do, but make sure everything's blanked off. Changing a component, the new component, make sure that any fluid that's inside it is drained out. You don't know how long it's been sitting. Yeah, so any storage fluid is drained out of the component. As it says there, when you're fitting pipes and hoses, just be careful for twisting and alignment and chafing and all the other good words that we've mentioned previously. And all the work that you're doing is obviously done in accordance with the AMM. Always follow the AMM because you're covering your own backside. If anything goes wrong, if you can say, no, I did it in accordance with, then nobody can touch you. If you deviate from the AMM and something goes wrong, you haven't got a leg to stand on. So always follow the manual. And if you think there's something wrong in the manual, flag it up to the management. Don't just go off and do your own thing. In this day and age, guys, cover your own backside. Yeah, nobody else will do it for you. So make sure you look after yourself. If you follow the manual, something goes wrong, as I say, there's no way you can get penalised for it. Yeah. What else are we doing? Yeah, seals. Yeah, if we change seals, always replace them with a new item. Never fit an old seal. And any seal is always identified by its part number. Don't just take 2, look at them, say they're the right size, because there are minute differences in sizes, in composition. Yeah, so always put the right part number about seal in. Seals are elastomeric, so we need to make sure that they're in date. So whatever the life is should be on the packaging. Just make sure that that's in date before you use them. The fitting tools we've got for seals, you get special tools for them, and they're like dentist's tools. Yeah, but they're specially blunt so that they're not going to damage the seal when we're fitting them. Your V and your U seals, we talked about those before. We mentioned them. Just make sure that they are fitted the right way around. Very easy to fit them back to front. If you're using them singly, yeah, where you're only wanting sealing in one direction, again, just make sure you've got it the right way around. And we talked about lubricating seals prior to fitment. Just make sure that they're soaked in system fluid. That one has come up as a question previously. Yeah, prior to fitting a seal, should you soak them in oil? Should you soak them in system fluid? Or should you cover them in talcum powder? Yeah, remember it's the system fluid prior to the seal being fitted. Yeah, storage. Yeah, the storage life of any component is determined by the non-metallic parts. So in the case of a hydraulic component, it's the life of the seals that are going to limit the component. So if you get one, always check that it's in date. Yeah. Any component that we fit into a hydraulic system needs to be functionally checked and leak tested prior to fitting. Inspect after installation, prior to test. Yeah. Once we've put the thing in, once we're happy with it, leak check it. Certain components need flow checks. Yeah. So making sure that we've got the correct flow rate from the pump and that the system is getting that correct flow rate. And the functional checks. Any hydraulic component that we replace needs to be functionally checked. Ta-da! And that was the hydraulic side of things. Has anybody got any questions on hydraulics at the moment? No? Deathly silence. I'll assume everybody's happy with that then.
Jim,
Yeah.
the chevron seals are the same, the V seals or different?
The what seals, sorry?
Chevron, CHEVRON. Sometimes I saw in the seals, that's why I'm asking.
Say that again.
Sometimes I saw in the books, that's why I'm asking. It's not in the notes, though I'm asking.
I've never heard of a chevron seal, I've got to be honest.
Okay then.
Yeah. What I would say,
Hello,
don't forget, guys, that the questions are going to come from the notes. Yeah. So you're working on whatever it is, ATRs, for example. Somebody else is working on Jetstream. Somebody else is working on 737s. Yeah. They're all different types of aeroplane, and they've all got their own slightly different terminology. What we're doing, we're teaching generic. We're just teaching the basic overall systems. So the terminology we're using should be common to every aeroplane. Yeah. So don't try to avoid using the terminology from your particular aircraft and use what's in the notes, because that's where the questions are going to come from. They're not going to come from the Jetstream manual or the 737 manual. They're going to come from those notes. Yeah, and they'll use the same language that's in the notes will be used in the questions.
Okay.
Okay. Thank you, Jim.
Okay with that?
Okay, Jim. I was going to ask that there is in a hydraulic chapter from this book. We did not find we did not but there is nowhere mentioned the closed system and open system. So I think that will not be important.
If it's not mentioned in the notes, no, they can't ask you a question on it.
Okay, Jim. Okay. No.
Yeah. Certainly a closed system and an open system, it doesn't in hydraulically it doesn't mean an awful lot, does it? Your hydraulic system needs to be closed, because you said if you had it open, you'd just creating problems. Anybody else got any questions there? Hydraulically.
Jim, can you
Yeah.
explain what patch testing?
Patch testing, yes.
Yep. Please.
That's yeah. The patch test. What we're going to do with the patch test, there's a kit you get, and that kit allows you to plug into the sampling point on the aeroplane and drain off an amount of oil. Yeah. So depending on the kit you get depends on the connections you get. Let's see if I can draw. Yeah. So with your patch test kit, you screw that onto the aeroplane connection, and there's a little pipe takes you down to a sample bottle. Yeah. And that sample bottle, yeah, has got a little pad inside it, and that little pad is a filter. So as oil comes out the aircraft, it runs through the filter, and then there'll be a fill line. Yeah, so that's your oil. Yeah, so you run a certain amount of oil through the filter, and then you close. There's an on-off tap on your connector, so you plug it in, open the tap. That allows oil through, throws through that little patch into the sample bottle. Once you've got the correct amount, close your tap off, disconnect your sampling kit, yeah, and then you can take your bottle away. What we do is we take the little gauze pad out, and we look at it. Where the oil's gone through, yeah, it's going to stain that pad, and depending on the severity of the staining, how dark the pad goes, depends how much contamination's in the oil. So using the example that's on the presentation slide there, yeah, what we've done with this one, we've gone in, taken a jar of oil, yeah, filled a jar up with oil, and now what we're going to do is pour that oil through these little filter pads. The filter pad just put onto a holder, if you like, pour the oil through, and the pad on that holder is going to stain. Then what we do is we just get a comparison chart, yeah, and the comparison chart has got different shades. So as we put the pads behind the comparison chart, we can see how dark it is, what degree of staining there is. If it's fairly light staining, yeah, classified as normal, there's no problem there. Sort of little bit heavier staining, it says abnormal on the slide, but what we'd do, we'd have a look. Yeah, that's quite heavy, and then we'd go to the recommendations in the book, And the book will say, for example, if it's between 8 and, let's say, 14, everything's fine, no action. If the staining's between 14 and 25, you need to carry out more frequent checks. Then if we've got really heavy staining, as in this case up at 63, yeah, it says critical. We know we've got severe contamination in the system. We need to do something about it. Again, we'll go to the manual. The manual will say, right, value between 50 and 70, system contamination. Now we need to replace the hydraulic oil or whatever it tells us to do. So that's what your patch test is. It's just a comparison, running a sample of oil through a little pad, yeah, seeing what color it turns and compare it to a chart.
Okay, Jim. Thank
Yeah.
you.
Anybody else?
Hello, Mr. Jim. Hello, Mr. Jim.
Hello, yeah.
So actually, I want to know one question about this hydraulic system, sir. I think this is not this question is not in this note, but this is my query for to know the answer, sir. Exactly, in the hydraulic system, sir, how the system will be operated in parallel mode or sir in series mode? Just I want to know, sir.
A hydraulic system.
Yes, sir. In a hydraulic system, the system will be operate in the parallel mode or in the series mode, sir. Because I have somewhere seen this question in the another book, so just for my knowledge only, sir. I want to ask.
Oh, I've never heard of a series or a parallel hydraulic system.
Means the system will be operate in
If
series system
your
or
emergency systems, okay, so if you've got two systems running, yeah, let's just give me a second. Right, that's a typical hydraulic system from a typical aeroplane. Yeah,
yes, sir.
you've got three systems. You've got a red system, a green system, and a yellow system, and each one of those is being run by a different engine. Yeah.
Okay, sir. Yes.
So you've got a reservoir for your red system with a pump, engine-driven pump for your red system, and that red system is feeding the nose wheel steering, the brakes, thrust reverse, spoilers, stabilator, and the rudder.
Yes, sir.
It's also into the elevators, ailerons, and again, spoilers and flaps. Your yellow system, yeah, is running at exactly the same time. So long as your engines are running, yeah, the engine-driven pumps are running, and that yellow system is feeding into those systems as well. So that they're running in I suppose in parallel with each other, if you want to say that. Yeah. If we've got a failure in the red system for whatever reason, then the yellow system is going to carry on operating those services. Likewise, the green system, again off its own engine, yeah, that is feeding into the other systems. If I had a failure in the yellow system, then the green system would take over. If I had a failure in the red system, yeah, certain elements, the green system would take over. So I'm not quite sure where series and parallel comes into it. I've got to be honest. I've never heard series and parallel referred to in.
No, sir. There is one question about this. About in the just YASA exam, in the YASA exam, I have seen this question. That's why I was confused about the series. That's why I asked with you, just for my knowledge on this.
Yeah, in all honesty, I've never heard it referred to as series or parallel. You could say parallel because they're all running together at the same time. So if you had a failure, everything would just carry on working smoothly. Yeah, so as I
Yes,
say, if you
sir.
had a failure in your red system, then your elevators would carry on. They would carry on automatically because the yellow system is running at the same time. So looking at it in that way, I'd say parallel, but I've never ever heard them
Yes, sir.
referred to as that.
Yes, sir. But this question is, sir, in the YASA exam, sir. YASA exam, but not in the EST, but in another type of exam.
All right, well, I refer you back to what I said before about the questions only coming from our notes.
Okay, sir. Yes, sir. Yeah. No, it's not it's from the EST exam, sir. This question is not from the EST exam, but from the another type YASA EU is from the some other category, I think.
Right.
But it
Okay.
belongs to YASA. Yes, sir. Thank you, sir. Thank you so much, sir.
Okay. No worries.
Okay.
Anybody else? All right.
Hello, Jim.
Yeah.
Okay. This now, can you again just explain shortly this modular valve assembly? There is one schematic given in book, and I am pretty much confused about this.
That one?
No. This is variable volume, but no, that was not.
Which
In the book there is
then?
one.
Which one?
Page number 102.
Well, the example, typical large hydraulic system.
Yes. Figure 101.
Right, I haven't got that on my slide.
Okay.
Yeah. If you give me a minute, I'll just try and put the notes up and talk you through it that way. Just give me a minute.
Jim, we'll discuss it next day or what?
What, that little diagram?
Yes.
No, I'll do it now. I'll just because I've got hard copy notes in front of me, and my hard copy that picture isn't on the presentation. I'll just pull up the PDF notes.
Okay, Jim. Okay, no problem.
Just give me 2 ticks. One I want. Right, is that showing up on your screen?
Yes, Jim.
You can see that little, it says typical hydraulic module unit, yeah?
Yes, Jim.
Right, is that the one you're talking about?
Yes, Jim. Yes, this is the picture which it is in the book, and I thought I would love to, I would like to get exp- get it explained from your side.
Well, all that's shown us when we talked about the modules, we said we can put lots of components into
Yes.
one place, yeah, which is called the
Yes.
module.
Yes.
Yeah. So on this one, yeah, all we've got is it's just showing us the pump pressure coming in. Yeah, that
Yes.
pump pressure going through a filter, the
Yes.
pressure filter. There's
Yes.
a low pressure switch, which will be one of these things up here. Yeah, saying
Okay.
that the pump's not producing enough pressure. There's a non-return valve, what they call a check valve. That'll be in here. It'll be one of these somewhere. Yeah, just making sure
Okay.
that the fluid's going in one direction. That's off system 1. Yeah, and then system 1 is, or system A, it's going off to wherever it needs to be. We've also got a line to the accumulator. Yeah, so we've got that emergency pressure, that storage of pressure, that damping down of pump pulsations, all the rest of the good shit. Yeah, so there's a feed to the accumulator that'll be felt there as well. The number 2 system, yeah, your pump pressure going in, filter, low pressure warning switch, check valve, exactly the same as we had before. Yeah, the only difference is in this system we've got that pressure relief valve. That'll be one of these, and there's a bypass valve in there as well. So the system pressure builds up. Yeah, that bypass can open and just allow any excess to go back to return. It's probably showing just the one side. Both sides, I would guess, will have the same facility in, but it's just showing that for clarity.
Okay, Jim. Okay. So the one side pressure goes to system A, other system B.
Yeah.
Okay. But the pressure feeding to both system will be same, I think, Jim.
This is coming from number 1 pump. This is coming from number 2 pump.
2 pump. Okay, but they are they are interconnected.
Yeah. Yeah, on this one.
One has they have interconnected, and there is pressure relief valve and bypass valve. And pressure feeding to both system will be same, I think.
Yes.
Okay.
Yeah.
And there is return line. And
yes.
This unit
that's just for the offload. Yeah. So if you get too high a pressure, the pressure relief will go and it'll just vent everything back to return.
So this is, I think, self-loading type, self-idling type of system.
It is,
because because it has got bypass and suction is there and pressure.
Yeah. Don't forget, all this is happening in the module. Yeah.
Okay.
If you're self-idling, when we talk about the suction, the pressure, and the bypass, you are looking at the pump. Yeah. How many connections has the pump got on it? If it's got 3 connections, it's a self-idling system. If it's only got 2, it's non-self-idling.
Okay, Jim, I've got this. That's what I have queried for. Only this is schematic diagram, which is now very clear. Thank you, Jim.
Okay, no worries. Anybody else got any questions, queries? Hydraulics, anything on hydraulics before we move on? Because that was the end of the hydraulics bit. We're about 20 minutes early. Yeah, so we've got 20 minutes to fill if anybody's got any questions.
Hello, Jim.
Yeah.
What about these questions which are in the back, 34 questions? These are quite relevant to the examination point of view or not?
Well, the revision questions, yeah. Yeah, there's no reason none of those could be made into some sort of multiple choice question. Yeah, so that they'd be very useful. And what I'll do, I'll send you some more questions out in a minute just to help you with your revision. But sort of examples, yeah, 22, 26. Yeah, 33. Yeah, all examples of the multi-choice questions.
Jim, questions I have not appeared for this for any exams taken by AST. So the questions will be like same to same, picking up one line and giving and asking a question, or it will be a kind of some.
Yep.
There will be
it's multiple choice, so you'll get a question with 3 possible answers, and you've got to pick the right answer.
Okay.
Yeah, that's
He's asking about. Hello, Jim. He's asking about the normally line by line or twisting the lines and being confused in examination.
Exactly.
Say that again. You've lost me there.
You get it?
No. Say again, please.
In the examination point of view, the AST will ask the questions like normally, like in the note that written, or they will twist the question and ask.
No, they'll just ask a question. For example, how might a self-idling pump be identified? It'll have 2 connections, 3 connections, or
or no connection.
Yeah, or a movable swash plate. Yeah, so you get a question like that. How could we identify a self-idling pump, 2 connections, 3 connections, or an adjustable swash plate? Yeah, so it'd be something along those lines, and then you've just got to tick A, B, or C. Has that answered your question?
3 connections.
Yeah, so how many connections has a non-self-idling pump got?
2.
2, yeah.
Friction and pressure.
Yeah, that's it exactly. So your question might be, how many connections has a non-self-idling pump got? 2, 3, or 7?
Three.
Yeah. Yeah, not
Self-idling.
Did I say non-self-idling? 2.
Self-idling 2, yeah.
Yeah, non-self-idling 2.
2.
Self-idling 3.
3.
Self-idling has got the bypass in it.
Yeah, self-idling.
Self-idling. Suction, pressure, bypass. And that is on the pump because the offload is happening internally on the pump. The non-self-idling. What do we need with a non-self-idling?
We need accumulator, ACOV.
That's it. You need the ACOV. And the ACOV has to have the accumulator.
Accumulator, yeah.
Yep. Anybody else got any questions at all?
Jim, just to remind for that, the tandem type you told me before lunch.
Oh, right. Yes. Yeah. Just give me 2 minutes. I'll do that now.
Okay.
Right. That should have appeared on your slide. The tandem actuator, yeah, is two separate systems working two separate actuators in one body. Yeah. Because the actuator is part of a subsystem, that's why it's not covered in the power generation side of it. But just for your peace of mind, we're going to run two systems into one actuator. The actuator split, but let's say the left-hand system's running, putting pressure in the actuator, it's going to move the ram to the left. Same with the right-hand system, pressure in, it's going to move the ram to the left. The other end open up to return. If I had a failure in the left-hand system, the right-hand system would still operate the actuator in the same manner, in exactly the same way. And that's your tandem actuator. Okay with that?
Yeah, thank you.
Yeah. And when you come on to do your helicopters, the actuators are covered as part of the flying controls and helicopters as well.
Okay.
Jim.
Anybody else?
The
Yes.
hydraulic supply is independent, eh?
Sorry?
In tandem actuator, the hydraulic supply is independent.
Yes, you've got two supplies, two systems feeding into one actuator, but the actuator is separated.
Okay. One is active and one is for standby, I think.
Not necessarily, no, you could have them both running at the same time, but the idea of the tandem actuator is if you get a failure in one system, the other one is going to carry on operating.
Okay, thank you, Jim.
Yep.
Only actuating cylinders are same, right?
In the tandem actuator, yeah, it's one body,
yeah,
with one ram, but with two pistons on. And if you get a failure in one system, then the second system can operate that actuator without any problem.
Okay, thank you.
But again, don't forget, don't get yourself bogged down in this. We're talking about power generation in hydraulics. How are we going to get the oil to the actuator? What actually happens at the actuator is for a different subject.
Okay.
Yeah.
Yeah.
Yeah, so with this, with the module that we've just done, that part 5, it's the generation. Yeah, so we're going from the reservoir to the pump via the filters, via the selector to the actuator. What's happening at the actuator in that subsystem is down for another lesson.
Okay.
Anybody else got anything? Right, if nobody's got anything there, what we're going to do is have a look at pneumatics. But what I'll do, we'll kick on with that after lunch. So I make it midday here. So we'll have an hour for lunch and then go through the pneumatic side of things. Okay.
Yeah.
Okay, Jim.
Hang on. What time do you guys normally come back? It's been 1900 your time, hasn't it?
Yeah.
So do you want to carry on and just have a few minutes extra for lunch and come back at 1900?
Sure.
Okay.
Yeah.
Sure, sir. No problem.
Yeah, that makes it
Sure,
easy,
Jim.
doesn't it? Yeah.
Yeah.
Okay, so 1900 your time. Yeah. We'll
Okay,
have
Jim.
a few
Okay,
extra
Jim.
minutes for lunch. So I will see you at 1900. If anybody's got any questions, then feel free. Okay.
Okay.
Okay, sir.
Okay.
Okay.
Enjoy your lunch.
Thank you. Pushpa. All right, just give the others 2 more minutes. And then we'll crack on.
Jim,
Yeah.
in the questions after the hydraulic system revision in our notes, can you see the 33, question number 33?
Yeah.
What's that? A bell valve or something?
Yeah, we looked at those in the filters. The filters, it's a bypass that allows fluid to flow straight past the filter if it's blocked.
Okay. No, I'm asking what is that bell valve? What is that?
It's the bypass valve in the filter. It's just the valve that opens to allow the fluid to pass straight through. So if you go to the page with the filters,
yeah. Here is also
whatever page filters are on, they were up near the front somewhere.
Page 37.
7.
filter.
Right, if you go to page 40, I think it is. Yeah, you'll see the picture of the twin element filter.
Twin element filter, yes.
You got that?
Yeah.
Yeah, and the bell valve is that little flapper valve there. So if the filters become blocked, if the two elements become blocked, yeah, normally that's closed, but if both elements are blocked, then that valve opens and allows fluid to flow through the filter unfiltered.
Okay, so that is called bell valve.
Yeah.
Okay, so the answer will be then twin element filter.
It's in a twin element filter, yeah.
Okay. Okay. I understand that. I just forgot the name, this bell valve where we pass through.
Yeah, we did mention it in passing, I'm sure.
Yeah, that's right. Okay, thank you.
Okay. All right. Hopefully we've got everybody back.
Yes, sir.
Let these two in. So if that's the case, we've got everybody back. We're all happy. Before I start on a new subject, though, has anybody got any questions on the old one? I'll send some more questions out for you either tonight or tomorrow. Probably tonight, if I remember. So I'll send some more pneumatic and hydraulic questions out for you to help you with your revision. But everybody seems to be on the right wavelength. Everybody seems to be thinking along the right lines. And when you've asked me a question, you've actually answered it yourself. So that's showing that everybody's got a good understanding going on. So if nobody's got any questions on hydraulics, what we're going to do for the next session is look at pneumatic systems. The pneumatic systems are very simple, very easy. Yeah. I'm duty bound to go through it, but pardon me, there's not a lot to pneumatics. Pneumatics divided up into sort of two sections, if you like. We'll look at light aircraft, smaller aircraft that have got compressors fitted, and those compressors providing pneumatic power to the aircraft. And we'll also have a look at the bleed air side of things. So the bleed air that's providing air from the engines, yeah, that's classed as pneumatic as well. So we'll have a look at both and drift through them. So we've got our hydraulic systems here. Some aircraft are going to use pneumatics. Advantage of pneumatics is that there's an awful lot of weight to be saved because we haven't got any return to worry about. Anything that's been used, the return side, we can just dump off to atmosphere. So there's no need for return lines. The pipelines themselves, because they're not carrying fluid, we can use smaller diameter pipes. Yeah, so we've got advantages there. Weight saving, smaller diameter pipes, return lines, we don't need those. And we're not having to carry about oodles, big reservoirs full of oil. We just take air from outside the aeroplane, use it for what we want to, and then throw it away again. Yeah. And we can use that air for lots of different systems. Yeah, utilize it for different systems. Sorry, I'll just let young Krishna back in. Yeah, so the air can use it for all sorts of things. Yeah, so it's quite handy. Smaller aircraft, yeah, we're going to take that air and bring it up to the working pressure that we want via a compressor. Yeah. When we don't need the compressors running, the compressor can be offloaded so that there's no load put on the thing. Yeah. We'll put a regulator in there as we draw, as we're running the system. We want it running at the correct pressure, so we use a pressure regulator to do that. We'll have a quick look at how that works. And we'll use relief valves. Again, most of the things that we've talked about here, we've talked about in the hydraulic side of things. Yeah, so when we come across the valves and the components in the system, a lot of them we're going to be familiar with. Lots of people joining in today. Right, so yeah, so smaller aircraft, yeah, we're going to stick a compressor in the aeroplane. That compressor is going to run. It's going to deliver our pressure for us. If we got sufficient pressure, we don't need any more. The compressor can be offloaded. Regulator is going to control that pressure. And again, we'll put relief valves in the system to prevent excessive buildup, as it says. How's it going to work then? Yeah, we're going to take air in from outside. Yeah, and obviously the atmospheric air, we need to make sure it's clean as we put it into the system. So it'll go through a filter before it does anything. Yeah, it'll then go into the compressor where it'll get compressed to the required pressure for the generation system. And then we'll push that on into the main pneumatic system via water and oil traps. Again, we don't want any contaminants in there. That air is going to be used for all sorts of things, so we need to make sure that it's free from contaminants. So we'll take the water and the oil out of it. We'll dehydrate that air, remove any additional moisture that might be in there. Filter it again, yeah, and then put it through a non-return valve. So once it's in the system, it's going to stay in there. Again, with our pneumatics, we can build in an emergency source of pneumatic power, and that emergency source will come from a separate storage bottle. We'll look at that in a minute. Isolation valves, yeah, we talked about those before. So if we want to work on part of the system without having to dump all the pressure, we can isolate various areas. And again, just like our hydraulic system, we're going to have indication for pressure. And that's all we need, really, isn't it, for our pneumatics. So a very basic pneumatic system. Yeah, we've got the filter. The filter is going to allow air through to the compressor. Yeah, from the compressor, we're going to send our air through the oil and water trap, on through the dehydrator, through a filter, through a non-return valve, and into the main system. Yeah. Again, another non-return valve to make sure that the air is going in the right direction. Up to a storage bottle, and that storage bottle is hoarding pressure. It's storing pressure for us until we actually need to use it. Yeah. Through reducing valves for our individual systems, if we need to, and then via our selector to whatever system it is. In this case, it's showing the landing gear. Yeah, so the air we're going to direct to undercarriage downline. We've got a test point, yes, so we can pressurize the system on the ground without running the compressor, so we can carry out any leak checks or whatever it might be. Warning light to tell us that the compressor's failed. Drain, so we can empty the oil and water traps. And then the other side, we've got an emergency bottle. Yeah. So from the non-return valve into the system splits, and as well as going to the main storage bottle, we will top up an emergency storage bottle. Again, that can be used to back up the main systems. So nice and simple system. Nothing to worth getting worried about. Nothing there that we need to worry about too much. The first main component, we've come through the filter, the first main component that we're going to encounter is the compressor. And the compressor is going to be either a 2-stage, 3-stage, 4-stage component. And it has what they call stepped cylinders. I'll show you those in a moment. Yeah, and those piston stepped cylinders have got stepped pistons that go inside them. Yeah, they work off a crankshaft, so each of the pistons is being run up and down off a crankshaft. Yeah, and they've got what they call integral coolers. The compressors you see on the slide are drawing in air, and that air is being blown over the motor of the compressor, keeping them cool. Older type compressors have fins on them. Bit like on a motorcycle engine, you get that finned effect, and all that's doing is increasing the surface area to increase cooling around the compressor. Right, so what's happening in the compressor then? As we say, it's a 2- or 4-stage compressor, normally 4-stage, and what we've got is these stepped cylinders. Yeah. What we're going to do is draw air in from outside the aircraft via a little non-return valve, and that air is going to sit in the chamber on top of the piston. Piston initially is at its low stroke. Yeah, ready to go. As the crankshaft rotates, yeah, the first piston, first stage, the piston is going to rise, and you can see how it's got quite a wide base area. As the piston rises, the air that was in the top chamber is going to get pushed through a non-return valve down into the lower chamber. Yeah, piston will come down. Yeah, and the air that was below it that we've just generated is going to get pushed again through a non-return valve into the lower chamber of the next piston, and you can see, hopefully, see that the areas are starting to reduce. So obviously, the smaller the area, the more we compress in the air, the higher the pressure is going. From there, yeah, from that lower chamber, the next piston comes down. Yeah, forces the air down through yet another non-return valve round into the top chamber, and again the stepping of that piston means that the area is being reduced, means that the pressure is going to, pardon me, going to increase. Ta-da! Yeah, piston comes up. Yeah, so now we've achieved that pressure through again another non-return valve, and the air's on its way into the system. Everybody okay with that? Yeah, so your first stage, air drawn in, top chamber. Second stage, into the lower half of that first cylinder. Third stage, from the cylinder into the lower half of the following cylinder. Fourth stage, yeah, up into the top chamber. And the fifth stage is off it goes. Dead easy, dead simple. Yeah, we're just stepping the the area is down. So as the air is transferred from one part to another, it is becoming compressed. As it compresses, its air pressure increases. We want to be able to control that pressure. Yeah, that compressor is banging on, running backwards and forwards. So we need to be able to control the pressure that it's churning out. And we do that by using third stage air. And when you get to that sentence in your notes, again, run a highlighter through it, please. Okay with that? So your air coming in, yeah, your number one piston, it's gone down, that air is going through into the number two piston, which is banging up and down in the number two cylinder. That third stage, yeah, as the air's coming into the third stage of the compressor, what we're going to do is take a tapping from there, yeah, and run that down, that third stage pressure, we're going to run that down to a little valve. Yeah, that little valve is sitting in the closed position, and it's sitting adjacent to a piston with a sort of needle nose on it. As the compressor's running, building up pressure, yeah, that pressure is off into the main system, and that pressure is being felt at the back end of our little piston. As the system pressure rises, it acts on the back end of that piston and pushes it forward and opens the third stage valve against a spring. So now, as that valve is opened, the third stage air is being allowed out to atmosphere. It's being dumped off to atmosphere. Obviously now that third stage air is causing a pressure drop. Because you've got the pressure drop, yeah, that's being felt at the back end of the piston. So now the spring is going to close off the third stage valve again. That will allow air to build up, get to the required pressure, and the whole process will start over again. But what you need to remember, what you need to stick your highlighter through, please, is the fact that the system is being controlled by third stage air. Everybody got that? Yes, Jim. So from our compressor, yeah.
Excuse me, sir. In
yes.
which chapter? Where is it, sir? In our book. Third, I got it, sir. Sorry, I got it.
You found it?
Yes, sir.
Okay. All right, I'm pleased you made me look. When you do your revision, yeah, the first page, the advantages of the pneumatic system, that's all common sense. Where we're going to use them, just different systems. Don't worry about all the individual bits. Yeah, just know that we're going to use it in various systems. All that stuff about pneumatics versus hydraulics versus electrics. Again, it's all common sense stuff, so don't dwell too much on that. And the high-tech applications, again, you don't need to memorize any of that. Just have a quick look so you've got an idea of what the systems are working against. Sorry, I'm just letting these guys into the meeting. Right, so we've put our air through the compressor. Now, obviously, that compressor is going to need lubrication. Yeah. Lubrication means oil in the compressor. it should be sealed, yeah, but there is always a possibility of some of that oil getting out and contaminating the air that's that we're trying to produce. I don't know who's just come in, but can you turn your mic off? Thank you. Not only that, we've taken air from the atmosphere and we've worked it, we've compressed it, and that's going to introduce moisture into the system. And we need to take that oil and water out of the air. The water especially because it's going to freeze, and as it freezes, it will block the system and prevent it from working. So, running it through the oil and water trap, the next component in the, pardon me, the next component in the line, yeah, very easy. It takes that air, runs it down a little chute, and that chute is cut off at an angle. It's just a pipe that's lopped off at an angle, and as the air comes in, it's caused to swirl, yeah. As it's swirling, yeah, and the fact that it's dropped into a larger area, that's causing that air to cool down and expand, and that and the centrifugal force is throwing any moisture and any oil out against the sides of the trap, yeah. That oil and water will then dribble down the walls and collect in at the lower portion of the trap. In the bottom of the trap, yeah, there's a little drain valve, and as it says on the slide there, that drain needs to be operated regularly to make sure that the oil and water trap is emptied. The air then that's being circulated around will go out through a gauze, just another type of filtration. Yeah, that air will be directed out. It'll go through that filter and off on into the system. So we've gone from the compressor to the oil and water trap. Again, because it's aviation, yeah, we're going to put that air through a dehydrator, which is going to take out any remaining moisture and prevent the possibility of that moisture getting in and freezing. The way we take that extra moisture out is to pass it through a desiccant. Now, the desiccant it mentions in the notes is activated alumina, and that again is worth sticking a highlighter through. I think it mentions silica as well in there, if I remember rightly. So as he swiftly having a look.
Not mentioned silica.
No, just the activated alumina. That's worth remembering. When I talk about silica, it's the same sort of thing. We get silica in dehydrators. We've got, yeah, so the air comes in, passes through the activated alumina where any moisture is absorbed, and again it goes out through a filter off into the next part of the system. That dehydrator, yeah, a lot of the desiccant that we use to indicate that the desiccant has got saturated with moisture, it changes colour, yeah, and I'm pretty sure it mentions it somewhere, but just make a note. If it doesn't mention it, I apologise, but I'm pretty sure it does somewhere. That desiccant, if it is blue, it's fine. Yeah. The more moisture it absorbs, it starts turning pink. Yeah, and once it's a pink colour, we know it's saturated with moisture and the desiccant needs replacing. Yeah, and what they do effectively is take it out, stick it in an oven, and dry it through. Yeah. So your desiccant, yeah, is there to remove any moisture. It says it's inspected and replaced it in accordance with the aircraft maintenance manual. Yeah, it mentions that, but I'm sure somewhere in the notes it mentions the colour. But if you just jot a note of it next to your diagram, at least I've pointed it out.
I think it's on the air condition, vapor cooling cycle. The descent silica gel.
Yeah, it might be. But the one that we're talking about, as I say, it could be silica, but the one it talks in the notes is this activated alumina. But just so we know that it's in good condition, we can tell by colour change. Every so often, yeah, inspect it, replace it in accordance with. Everybody okay with that? Any questions, queries there? No. All right. From there then, yeah, we're going to go down to our pressure relief valve. And we've talked about the pressure relief valves, was it yesterday or Friday? No, must have been Friday. Yesterday was Sunday. Doesn't time fly? The relief valve, yeah. It's exactly the same that we saw with the hydraulics, where we're going to get system pressure bowling down the pipeline. If that system pressure builds up, it's going to lift a little seat against a spring. As it lifts the seat, it's going to allow any excess pressure to dump out to atmosphere. Yeah. The pressure relief valve, again, the same as we saw before, is adjustable. Yeah, it's just screwing down a little cap against the spring, and obviously the more you compress the spring, the harder it is for the valve seat to lift. So these pressure relief valves dotted about the place, we need to ensure that we get the correct pressure relief or the correct pressure setting for the system that we're fitting the valve to. So again, it should only go off part number. When these things are adjusted in the workshop by the workshop people, they'll adjust it, they'll set it, they'll fit the circlip to lock the thing in place, and there should be a little plate on the side that tells you the part number of the relief valve. So just make sure that you check you've got the right one for the right system. Don't just pick a valve up and say, yeah, that'll do. Yeah, right relief pressure for the right system. So we go through the relief valve or past the relief valve. So long as everything's happy, that's going to remain seated, overpressure, lift, dump. And then on to our filter. The filter in the system, yeah, again, it says the element materials may vary. It does, it depends on the pressure that we're running through. Most of the ones that I've come across are a sort of felty material. But as it says, the element materials can vary. And again, with the filter, what we're going to do is go through a set of perforated plates, just little plates with holes in them, and between those plates we've got our filter element. Yeah, the air passes through the filter pad and on into the system. That filter, because it's our last line of defense now, needs to be checked for the presence of moisture. And if we've got moisture present in the filter, it means our barriers prior to the filter have failed. So we need to do something about it. Pardon me. So onto the system, from the filter through a check valve into our storage cylinder. The air storage cylinder, is a bottle, and that bottle mounted in the aircraft with straps. It's topped up constantly by the compressor. So every time the compressor runs, it's charging that bottle up and making sure that the bottle has got plenty of pressure in it. That's stored compressed air, providing initial impetus to a system. It's a bit like our accumulator, in as much as you've got that head of pressure there. So as soon as you select a system, there's a head of pressure ready to operate it. It says they're wire wound for strength, and they are. Around the bottle, there should be wire wrapping. That wire wrapping is there, A, to give the bottle a bit of strength, and B, if we get moisture in the bottle, that moisture, we can't see it, it's going to start to corrode from the inside. And if you've got 3000 psi in there, or whatever psi, and the structure, the material fails due to corrosion, that's going to be quite explosive. And the idea of wire wrapping the bottle is, if there's any explosive force, that wire should contain it and prevent debris and shrapnel going everywhere, creating mayhem. So the bottle's wire wound for a bit of additional strength. Because of that possibility of moisture and corrosion, they are normally mounted in the upright position. So if we do get any moisture in there, it's going to dribble down the sides and accumulate at the bottle head. And on the bottle head somewhere, there should be a little drain, so we can check just to make sure that there's no moisture entering the system. The other thing that we find in the bottle are stack pipes. And the stack pipes, as it says there on the slide, are just there to prevent any contamination entering the working system. It's exactly the same principle as we had before. Any contaminants should sink to the bottom of the bottle, and not be dragged out. So if that's your bottle head mounted upright, the air will exit via a stack pipe, and any contaminants that are in there will sink to the bottom and they can't get dragged out. There's also a little stack pipe in there, and that other little stack pipe will take you to your gauging point to tell you what pressure you've got in the bottle. Okay with that? Just give me 30 seconds. I'm just going to have a quick look, make sure I missed anything there. All right, so compressor. Everybody happy with the operation of the compressor? Pistons moving up and down, compressing the air, building the pressure up, and then allowing it into the system. The pressure regulator is controlling the pressure allowed out, and it's offloading the system when we don't need any power. That regulator using third stage air. System service operated, pressure system drops for any reason, that bore valve will close and the compressor will run to full system pressure. Oil and water trap removes any oil or water. Throws the air around, circulates it, and any oil or moisture thrown out to the sides and dribbles down to the drain area. Dehydrator Yeah, removes any moisture. That moisture could freeze at altitude and block everything up. Corrosion we've mentioned, so we need to get rid of it all. And the activated alumina is the desiccant we're going to use there. Filter takes out any solids, any residual oil vapor. Little perforated plates with a pad between them, the filter pad between them. And in the bottom of there is, again, a drain. Relief valve, we mentioned the relief valve, prevents system pressure from exceeding the normal maximum. Happy days there. And the storage cylinder. Yeah, systems are operated. The cylinder will provide the initial impetus to the system. Cylinders made of steel, usually wire wound, extra strength, mounted in the upright position, stack pipes for the supply and the gauge points to prevent any contaminants getting passed out. Drain plug, yeah. If we find moisture in there, we're in a world of pain, so we've got to watch for moisture in there. That gets drained regularly to check. Cylinders contain high pressure, so any operation of drain valve plugs always follow the maintenance manual. Yeah, do what that says. Boom.
Jim,
Yeah.
can you please explain once the stack pipes, how it prevents the moisture or something? The stack pipes operation, please.
Yeah, just give me 2 ticks and I will come on to them. Again, yeah. High pressure air is dangerous. Yeah, it can kill. As you know from your module 7 and all the rest of it, if you get air injected in your skin, air bubbles in your blood, that goes to the heart. Your heart cavitates, stops beating, and that's really going to spoil your day. So always, always, always follow the maintenance manual instructions. The cylinders themselves need testing at regular intervals, and the date that they were last tested should be stamped on the neck of the bottle. Yeah, now it does mention the neck of the bottle. Please stick your highlighter through that. Sometimes you might get a question saying, if it's not stenciled on the bottle, where could the test date be found? And it's stamped on the neck. As it says in the notes, sometimes we'll find that the test date is actually stenciled on the side of the bottle, just to give us a better clue. But that's your backup. Also, the bottles are lifed, so they should come with their own log card. And after so many years in service, the bottle's withdrawn and it's sent off back to the manufacturer for a kind of overhaul and inspection and what have you. That's the wire winding I was talking about. Yeah, wrapped around the bottle. So if anything does go awry, that wire wrapped around there is going to contain any explosive force. The stack pipes you've just asked me about are little stand pipes that sit up from the neck of the bottle, and the reason they're there is to prevent any impurities, any moisture from being taken out into the main system. Very, very similar to our hydraulic reservoir. Yeah, the air that comes into the bottle, yeah, if we want to take it out, it's going to go out through the stack pipe off to where it needs to be. And because it's going off to out via the stack pipe, any impurities, any contamination is going to be below the level of the stack pipe, so it's not going to get dragged out with that air. Likewise, for our gauge connection, small stack pipe there, and again, that's just preventing any crap getting into the pressure gauge and giving us false readings or giving us no reading or whatever. Also in the head of the bottle, Yeah, as you can see, little drain plug there, and that period specified. We dump the pressure from the bottle, take that drain plug out, and make sure that there's nothing untoward comes out of it, such as moisture. Again, hopefully you can see on the neck of the bottle there, the date stamped on it when it was last tested. And those cylinders, if they're left to their own devices, can be very very dangerous. Yeah, we need to make sure that they're monitored and looked after. This particular one was a 747. I think it was flying from Indonesia to Australia or the other way around. And just in the middle of the flight, there was an almighty explosion. The aircraft landed safely, nobody injured. But when they inspected it, they found a huge chunk out of the fuselage. What had happened, there'd been a pneumatic system used years ago, and it had been disconnected, isolated, but it had never been depressurized. And over a period of time, the moisture in that system had eaten through the wall of the emergency storage bottle, and eventually the bottle gave way and it exploded, and that was the result. Yeah. So again, they might seem like niff-naff, they might seem easy, obvious systems, but they are dangerous. We do need to be aware of them. We do need to keep our eyes open. Everybody okay there? Any questions there at all?
These cylinders are always the drain at the bottom?
Yes. Yeah, because moisture is not going to flow uphill.
Okay,
yeah. So
that is the upright
gravity's...
position.
Sorry?
That's the upright position you were talking in the notes?
Yes.
Okay.
Yeah, so there will be exceptions. I say they're normally mounted in the upright position. You can guarantee you'll go to an aeroplane somewhere and you'll find it mounted in the horizontal or at a different angle, but they should be, wherever possible, mounted in the upright position with the head at the bottom. So if you do get any contaminants in there, they're going to run to the bottom. Yeah. And that with the stack pipe is going to prevent those contaminants from being released into the systems.
Okay.
All right.
Yeah.
Anybody else at all?
Yes, Jim.
Yeah.
How the stack pipe and stand pipe, it seems that they have common function?
They are the same thing. It's just a different name for the same thing.
Okay, that means they are the same thing, but due to the ATA chapter, they are different name?
Just different names, yeah.
Okay.
Stack pipe, stand pipe, same thing.
Okay. Thank you.
Anybody else got any questions there? Right, some of the valves that we'll come across then, because it's in the book, I'll kind of slide over the internal workings, but we need to know what the purpose of these particular valves are. The first one is the pressure reducing valve, and the pressure reducing valve is there to bring main system pressure down to usable levels. Yeah. And all this is just a little, well, it says a plunger there. It's a little piston operated on a lever. Yeah. And a set of bellows there just to compensate for altitude. What's happening the low pressure side of the system, is being felt on this little plate, and the little plate connected to a set of bellows. Yeah, the external pressure on the bellows, obviously compressing and expanding, and as that low pressure is acting on the bellows, it's pushing up on this little well, it calls it the head plate. As the head plate moves, it's opening or closing the high pressure inlet. So as the high pressure inlet opens, allowing more high pressure in, again, that's going to be acting on the bellows, low pressure side of the system, acting on the bellows, and the spring is adjusted so that the reducing valve maintains the correct pressure. Yeah. There's not a lot else I can say about that. You know, it's just opening and closing the high pressure valve, admitting the correct amount of air at the correct at the higher pressure. The low pressure system, again, feeling on it, so that the two are balancing each other out. Pardon me. Didn't sleep last night. Yeah, so we adjust the screw. Yeah, that adjusts the pressure on the plate and keeps it at the right position. If the bellows starts to rise or fall because the low pressure is too much, too little, yeah, the inlet pressure will just modulate and keep everything right. So we don't need to know about the internal workings. That was just for your benefit when you're looking. But the pressure reducing valve is there to reduce pressure from the generation side to the required pressure for subsystem. The pressure maintaining valve. Now, remember I said the other day when we were talking about the hydraulic version, what was the hydraulic version called?
Priority valve.
Priority valve. Good lads. Yeah. Please, please, please keep that in mind, because the exam questions could be worded priority valve, pressure maintaining valve. Yeah. Depends what question comes out of the bank, but they are both performing the same function and they are both operating in the same manner. Yeah, your pressure that's being supplied from your air bottle, so long as there's no leaks or anything, it'll provide primary and non-essential services. When we're talking about essential services with pneumatics, we're talking about things like landing gear. We're not talking flying controls per se. Some older aircraft, they used to use pneumatics for operating the flaps, yeah, which would be considered an essential service. Your brakes probably an essential service. So they're doing the same thing. Whatever's considered essential for your aircraft type, yeah, they'll be fed. Likewise, the non-essential services. If you get a pressure drop for whatever reason, the spring will close the valve, yeah, and it will seal off the non-essential side and prioritize the essential services for the feed from the bottle. All right there. Ting ting. Yeah.
Excuse me, sir.
Yeah.
Excuse me, sir. In exam point of view, if the both options are there, what will you be the good answer?
Say that again. I couldn't hear a word you were saying.
For exam point of view, if these questions comes and options are both priority valve and the essentially that pressure maintaining valve, which is
You won't
good
get the two. You will have something along the lines of, what is the purpose of the pressure maintaining valve? Is it to maintain system pressure? Is it to protect your essential services? Or does it direct fluid in one direction? Yeah, you won't get any confusion in the naming. The confusion arises if you don't know that the pressure maintaining valve and the priority valve are the same thing.
Okay, thank you.
Yeah.
Yeah.
Hello, Jim.
Hello.
I couldn't get this pressure reducing valve. You know how pressure reduces?
You got high pressure coming in, yeah, and there's an inlet valve allowing air into the system.
Okay.
Yeah. You've got the low pressure side of it. Hang on, I'll just I'll go through it step by step to make sure that we've. Yeah. The spring in there is your datum. You're going to set the spring for the pressure that you want your system to operate at. Okay.
Okay.
You've got system pressure acting on the bellows on one side. Yeah. Pressure in the operating system is lower than the valve setting. The compression spring extends, moves the inlet valve plunger to admit more air into the system. Yeah. Pressure in the system increases, acts on the bellows, causes it to compress, and that inlet valve will move to seal off. So what that's saying essentially, that's your inlet valve, that's your high pressure side, this is the low pressure that you want. You've got a bellows evacuated to atmosphere internally. You've got a spring that's adjusted to the required pressure. Yeah?
Okay.
Your low pressure system, yeah, that pressure is acting on the bellows. Yeah. If that pressure drops, yeah, the bellows are going to start to shrink, I think. So the plate head is going to reduce. Yeah. So what happens is as the plate head moves, it's caused via that little linkage. It's causing the inlet to open. As the inlet opens, yeah, it's allowing more pressure in. The more pressure you get in, that's going to act on the bellows. Yeah. As the bellows expand, it's going to close off the inlet valve. So in doing that, it's maintaining the pressure out to the low pressure side.
Okay. Thank you, Jim. Got it.
You see that okay?
Okay, Jim. Thank you, Jim.
That's all right. Anybody else in there? Pressure maintaining valve, we talked about that. The isolation valve, yeah, the isolation valve manually operated, so that there's a lever on there that you can open and close the system with, and it allows us to work on a part of the subsystems without having to empty out the storage cylinder. Yeah. One of the things that you've got to ensure, if you operate that isolation valve, you need to record it on the job sheet that you're filling in. Yeah. And that way, the closed valve, you can make sure that it's reopened before the aircraft goes flying. They're normally wire locked in the open position. The handle's wire locked in the open position. So again, that's something you can record on the paperwork. Again, as we've said 2 or 3 times now, before any work is carried out, ensure that the system is depressurized. Yeah. With a pressurized hydraulic system, you're going to get a face full of oil, which is going to do you damage. With a pneumatic system, if that air pressure gets injected into your skin, it can be fatal. So make sure before you do anything that your system has been depressurized. The isolating valve, yeah, just a little switch that will open or close the system. Yeah, if we operate the cam, the inlet valve will press down against the spring, it'll seal off. So any air coming in is just stuck in the valve. It can't get out. Once we release the operating cam, the valve will open and allow system pressure through to the outlet, whichever way it's operating. Right. Again, I'm kind of duty bound to go through this, but it's a system. We don't need to know the ins and outs of it. I just need to point out the various components that are in there. But because they're in the book, I'll just go through the workings of them very quickly. One of the systems that will operate is the landing gear, yeah, the undercarriage. And that undercarriage system, operated by pneumatics, will select up or down, whichever side we're pressurizing will operate, and the other one will be open to atmosphere to return. Excuse me just a second. Oh, yeah, pardon me, I do apologise. Obviously, your selector valves are what is going to direct the pressure to one side of the actuator or the other. The actuators, yeah, are going to convert your pressure to linear or rotary motion. In this case, we'll just call it an actuator rather than a motor. But the actuators are just take that pressure and give us an output. Exactly the same as we saw in the hydraulic system. We'll have an emergency source of power, which is that other bottle we saw. If we need to select the emergency source to swap the primary to the secondary, we'll use a shuttle valve. Exactly the same as we saw in our hydraulics. Yeah. The valve, it says, as I said before, we don't need to worry about the internal workings, but we know that the selector's there. We've got an air supply coming in, operated by the valve operated by a solenoid. So when I make a selection, the solenoid's going to operate. In this case, air supply coming in. That solenoid's closed. Yeah. So the air is going to be directed down to this one. As the air comes in via the open solenoid, it's going to go into a lower chamber, which is going to push down on a piston. As we push down on the piston, yeah, that's going to operate a beam. Yeah, at the same time, as this piston comes down, we're going to seal off the sorry, we're going to allow air pressure around to the undercarriage upline, so the undercarriage will be retracted. At the same time, because we've got the thing on a pivot here, yeah, the opposite side of the selector, the piston's being pushed up. As the piston pushes up, yeah, it closes off the line and allows this downside to vent out to atmosphere. Yeah, so the upline is pressurized, the downline back out to exhaust. Yeah. And again, if we make the opposite selection, then that solenoid will energize, air will be directed through into this top chamber. That'll push down on the ram. Yeah, as the ram pushes down, it'll push down on the spring, seal off the downline, allow that to allow that air, sorry, to go to the downline. It'll then open the upline up to exhaust. Okay with that? We need to know that the selector is going to allow us to have an up selection and a down selection. We don't really need to know the internal workings, but I'll go through it there because it's in the notes. The actuator, yeah, that air is going to travel off to the actuator, and the actuator similar to our hydraulic actuator. It's got a ram, yeah, air acting on one end of the ram. It's going to push the actuator, the other side open to return, swap them over, yeah, the air coming in, pushing on the other face of the ram, pushing it back, and the opposite end open to return. The thing we need to remember with the actuator, and it might come up, is the damping mechanism. If we didn't damp that actuator, you've just got all that pneumatic pressure pushing the ram backwards and forwards. With our hydraulic system, we put in restrictors into the supply line to the actuator, which slowed down the operation. With our pneumatics, the way we do that, the way we slow down the operation, is by grease. We use grease as a damping medium. Yeah, the way it operates, we've got a fixed piston, yeah, with a little rod, yeah, holding it to the cylinder. That little piston lives in grease one side and the other of it. As the ram extends, yeah, so let's say we put pressure in this end. As we push on the ram, yeah, that ram is also trying to push grease through a little hole in the end of the piston. Yeah, so the actuator can only extend as quickly as the grease can go through that little orifice. Just behind the orifice, there's a little free-moving plate. Yeah, so as the grease is trying to travel this way, that plate is going to block off part of the hole. Yeah, so that now we've slowed down the actuator of the rate of that actuator. On the flip side, on the upside, again, as the actuators try to retract, yeah, it's going to it needs to force grease from one side of the piston to the other. So as grease is going through that little orifice, again, the actuator can only travel as quickly as the grease can go through. That little floating plate, yeah, because the grease is going the opposite direction, yeah, it's pushing the plate back, so it's opening the orifice so that the actuator can travel a little bit faster in one direction than the other. So if you think about that as an undercarriage actuator, which direction of travel do we want to be the slower?
Down.
Rearward, down, yeah.
Down, yeah. Because coming up, we can come a little bit quicker. We want to get rid of all that drag on the aeroplane. Yeah, so we'll allow it to come up slightly quicker. When we're lowering it, we want a nice, controlled, steady movement, so we're not putting any huge vibrations through the airframe. So yeah, so the cylinder extends. Yeah, as that cylinder's pushing forward, it's pushing grease through the orifice, through the little hole, the damping plate closing off part of that hole to give you slower operation in one direction than the other. Out of all that little lot, the thing that you need to remember is that the damping is done internally in the actuator by grease. Okay with that? Sound, right. Your shuttle valve, yeah? We talked about shuttle valves Friday in our hydraulics. Normal supply comes in, off to wherever it needs to be. If I get a failure in the normal supply, the backup emergency supply is selected. As that is selected, it's going to push the shuttle over, seal off the entrance for the normal, and allow your secondary source to take over. Yeah, so your normal supply, that area is sealed off. And all it is, as the name suggests, just a little shuttle that moves backwards and forwards in a cylinder. So now your emergency supply is feeding your service. God, I hate this. The brake control valve, yeah. Pneumatic, a lot of smaller aircraft will use pneumatic brakes. And via the brake control valve, again, it's very similar to what we've seen. All we're doing is allowing the air to go in the required direction. Obviously, with our brakes, it's going to be brakes on or brakes off, but you've got two of them. Yeah, so we're going to direct air, two outlets to one side, two outlets to the other side. Yeah. So we're directing the fluid to the brakes. The brakes operated by the rudder pedals. Yeah, so the pilot will press on the pedals. As he presses on the pedals, yeah, via this this beam, yeah, is moving the lower cylinder against a spring, pushing it up. As he pushes that spring up, yeah, this little exhaust valve is being sealed off. As that exhaust valve is being sealed off, it's also raising this second valve. So air pressure coming in, yeah, is now going to be allowed to go down to the brakes, pressurizing the brakes. The harder I press the brakes, the more this is being compressed, the more air is being allowed, so the more braking efficiency you're going to get. As I start easing off on the pedal, yeah, as I ease off, this exhaust valve starts to open, and likewise the inlet valve starts to close off. As the exhaust valve starts to open, yeah, the return from the brakes is allowed to vent out to atmosphere. So pressing on the brakes, yeah, all we're doing is operating the internal mechanism in the brake control valve. That's sending off pressure to the left-hand and right-hand brake units. Yeah, and as I back off again, I'm opening them, relieving the pressure. There's not as much pressure on the brakes. Yeah. And the excess is being allowed off to atmosphere. Everybody okay with that? Can you see that okay? Yes, Jim? No, Jim?
Break, sir.
Jim,
Yeah.
This is rudder pedal, brake pedal. So this is in the
rudder
position
pedal
of
and the
off.
brake pedal are the same thing, aren't they?
Yes, sir. Yes, sir. Is this is in the off position, I think.
It's a what?
This brake is in off position. This schematic diagram is showing.
See that little arrow there? Yeah, that's saying that you're pushing down. If you push the top of the rudder pedals, that's
Yes.
where your brakes are.
Yes.
Yeah, your rudder goes backwards and forwards. Your brakes, top to bottom.
That
so if I push down on the rudder pedal,
yes.
Yeah. What's happening is this one's showing off. Push down. That little inner sleeve is pushing up and closing off this exhaust valve.
Okay.
Yeah. As it closes off the exhaust valve, that's pushing up on this little grey thing here. Yeah.
Okay.
That little grey thing, the inlet valve, is now allowing pressure through to the brakes.
Okay.
If I back off, if I reduce the pressure on the pedals, yeah, this thing's going to start to drop down again. Yeah. Which aided by spring pressure is pushing the exhaust valve down, which is allowing the inlet to start to close off, and at the same time is allowing exhaust pressure out of the brakes. Yeah, so as you ease off the pressure on the brakes, yeah, that excess pressure is coming down here, but this cap is pushing down. So now the excess pressure going out and off to overboard.
Okay, Jim. Thank you.
You sure?
Sure, Jim.
Excellent. The only other thing we need to say on that is the parking brake handle. Yeah, if we press down on the rudder pedals, apply the brakes, and then pull the handle, the parking brake handle, that's going to hold the brakes in the on position. Yeah, so there's always going to be a pressure feed down to the brakes until we let the parking brake off again. The brakes are going to be on. Yeah. God. Again, we don't need to worry about this. Just what's happening when we make an undercarriage selection. We've been through the pressure reducing valve to bring us down to normal system operating, through the selector into the downline. From the downline, we're going to go to our actuators, and the actuators are going to extend. As they're extending, yeah, the selector's open, yeah, via the exhaust valve. Selector's open, and any excess or the I say excess, the return pressure is just dumped to exhaust. Yeah, there's an emergency facility there if we need it. We can pull an emergency handle, yeah, and that will allow pressure in from the emergency side of things. Yeah, but your undercarriage selector, that little solenoid that we talked about, yeah, up or down, and all that's going to happen is the selector is going to swap round, and then allow pressure in whichever side of the actuator, extend or retract, and the other one's going to be opened up to atmosphere. Yeah. Your up selection, yeah, selector turned round, your up selection now up to the other side of the actuators, pushes the actuator, and your exhaust line is now through that non-return valve, and again out to atmosphere. We don't need to worry about the schematics. Right, that's a brilliant place to stop for a cup of tea. That's 14:30 my time. We'll have 20 minutes, so we'll say 14:50, 20-minute tea break, and then we'll finish off the pneumatic systems. Unless anybody's got any questions in the meantime. No? Okay, right. We'll have a tea break today because I'm absolutely gagging for a cuppa. So I'll see you in a few minutes.
Okay, Jim.
Okay.
Okay, Jim.
kitchen.
All right, well, enjoy yourself. See you later. Don't forget the torch. Enjoy.
Yeah.
What time are you back?
Yeah, I don't really know tonight, and that's why Lucy doesn't know them to walk down. Know what time will be finished?
Okay. Well, she wants to just do the half field with me.
Yeah. I'll say to her.
All right. See you later.
I might just give her a ring if I get so far done and then know how long I've got to be.
Uh huh.
If that makes any sense. If I can guide, then when I've ridden, I'll be about an hour washing his bits and pieces, his feathers and stuff.
All right.
So I'll see you after that.
All right then. Take care. Oh, dear. Okay, thanks. Right, hooky cookie, picking a pokey. Have we got everybody back?
Mm-hmm.
Yeah, looking good. Lovely. Right. Last little bit in our pneumatic adventure together then. We've had a look at the smaller aircraft and said that they're going to generate air using a compressor. And that compressor trundling away and supplying air to a storage bottle. Storage bottle is going to be used to hold that air and then supply it when a system needs it. And the compressor is constantly topping the storage bottle up. With our larger aircraft, we're going to use engine bleed air. Yeah, engine bleed air, again, it's a free source of air. The engines are taking in far in excess of what they need. Yeah, so that the air not required by the engines normal times, yeah, we're going to tap into that. So we'll grab air from the engine and use it for what we need. Yeah, we're going to take it from the low or the intermediate stages of the compressor. Yeah, I can't remember the stage numbers. They're around about stage 9, I think. You might well see bleed air referred to as charge air. Yeah, charge air, exactly the same. It's just different terminology. But you might see bleed air and charged air referred to together. And another source of air, we could use the APU. Yeah, remember when we talked about conditioning the other day, and we said about the APU? Yeah, that's another source of our bleed air. That air coming off the engines, though, out of the compressor, the engine, it's pretty hot. Pretty hot. So what we need to do is to control the temperature of the air that we're going to pump into the system, yeah, and control the pressure of the air that we're taking off as well. So we'll have a look at how we go around, how we manage that. Excuse me, I'm just somebody wanting in? No. Right, first thing we're going to do then is take the air from the engine and we're going to run it through what they call a pre-cooler. And the pre-cooler is the first point of cooling for the air on the large aircraft. Yeah, I'm going to control that using a temperature thermostat. We'll have a bleed air over temperature switch in the system to make sure that the temperature coming off the pre-cooler is correct. The high stage valve, yeah, as part of the bleed air system, we've said that depending on the demand on the engines at the time, yeah, if the aircraft's sitting in the cruise, no demands on the engine, not doing anything, there's buckets of spare air. So we can take the air from one stage of the compressor. If there's a big demand on the engine, let's say we're in the middle of takeoff, yeah, we don't want to spoil the performance of the engine. So what we do is alter the position where we're position on the compressor where we're taking the air from, and the high stage valve allows us to do that. Regulator, yeah, again, we need to make sure that the pressure that we're putting into the system is within limits. So we're going to have a regulator in the system, and anywhere where we've got pressure, where there's a possibility of pressure building up, we'll stick a pressure relief valve in. Yeah, pressure transmitter in the system to the cabin so that the crew can see what's going on. So right, ting. Did that. Next slide, please. Right, our basic bleed air system. Yeah, and what I'll do, I'll keep referring to the notes on this one to make sure that I'm going through the components in the right order. I'll make sure that I don't miss anything that we're talking about. Right, so our basic system. Yep. First thing we're looking at is the pre-cooler. Yeah. And the pre-cooler is where the initial cooling of the air that we are going to take from the engine is going to occur. Yeah, so let's say we're on the HP stage of the engine. Yeah, via the high stage valve, and the high stage valve is going to either open or close the HP, or open and close the intermediate stage. Yeah. Via a pressure regulator and shut-off valve, basically the on-off valve for the system, that hot air that we're taking, we're going to run up to the pre-cooler. Yeah, the pre-cooler, in this instance, is using cold air from the fan of the engine. So we're pushing hot air across one way, cold air from the fan of the engine the other way, and that's how we are bringing the temperature of our bleed air down initially. Ta-da! Right. What we're going to do is we're going to have a what they call a pre-cooler control valve. Yeah, and the pre-cooler control valve is being modulated, should we say, by the temperature that the control valve senses in the duct. One for your highlighter is that the pre-cooled air needs to be maintained around about 230 degrees C. Yeah, cools the bleed air to, it says 200 to 230 degrees C. We want it around 230. Yeah, that pre-cooler control valve modulating in response to a temperature sensor located downstream of the cooler. So what we've got a 230 degree thermostat, we've got the pre-cooler control valve. As temperature starts to rise, the pre-cooler control valve will sense that and it will start to open the control valve. The control valve will then allow more cold air across the pre-cooler. As that cold air comes down, yeah, the pre-cooler sensor will start to back off the control valve. At the same time, yeah, we've got a 230 degree thermostat. That 230 degree thermostat is monitoring the temperature of air in the duct. If we get a failure in the cooling valve, pre-cooler valve, yeah, that thermostat will start to shut off the hot air via the pressure regulator shut-off valve. Yeah, so that will back off on the hot air. So the system is kind of balancing itself, modulating itself. Yeah. So again, pre-cooler cools to 200 to 230. The pre-cooler control valve modulates in response to a temperature sensor located downstream. Don't worry about the internal workings of the sensor. I've never come across that. Temperature limit thermostat. The limit thermostat has got a temperature sensor in it. Temperature in the duct reaches 230. It'll reduce the control air pressure at the bleed air regulator, which in turn will cause the shut-off valve to start to close, which in turn will reduce the amount of hot bleed air passing through the pre-cooler. Bleed air over temperature indicator, yeah, looks at an over temperature switch downstream of the pre-cooler, connected to a warning light and the control panel. And if we reach 255 degrees C, yeah, then the system will shut down. It can be reset once the temperature has reached an appropriate level. Yeah. So again, your 255 switch, yeah, coming out the pre-cooler. If we get up to 255, the overheat switch will, via the bleed air regulator, trip off the shut-off valve. That'll close it all down until that temperature is reduced. There'll be a warning light in the cabin. Once the temperature is reduced to an acceptable level, the warning light will go out, and the pilot can reset the system, open the valve up again. We've mentioned the HP stage, yeah. So when there's no real demand on the engine, we can take pressure from the high pressure stage of the engine. If there's a big demand on the engine, yeah, we can take that from the intermediate stage, again via a check valve, relief valve, and through the shut-off valve. Yeah. Just looking on there, anything else I need to mention? Not really. You can see, again, we talked about this the other day, hot air from the engine is getting ducted straight off to your anti-icing. We've talked about that. We've talked about that. Talked about that. That's just looking at the pressure, regulating that, which in turn is looking at what is effectively the on-off valve. High stage valve we know about, 2 stages. pre-cooler control valve we know about, and the pre-cooler itself. Has anybody got any questions on that?
Jim, in the book, hello?
Yeah.
Hello, Jim.
Yeah.
Jim, in the book, it is mentioned air is tapped from low or intermediate stage compressor. But in the schematic diagram here, we can see it has been tapped from high pressure compressor.
Just have a look. Yeah. Typical system, figure 16. The main supply of the compressed air is provided by the low pressure intermediate stages of the engine compressor. At reduced power settings, the high stage valve will open to allow the high pressure compressor to satisfy the demands. Yeah, so normal operation, yeah, the main supply of compressed air from here. Yeah, and at reduced power settings. So when we're at it's just way around to me. I said that when there was a high demand on the engine, yeah, we're going to take from the intermediate stage. When there's no demand on the engine, so when we're at cruise, when it's producing excess air, yeah, we're going to switch over via the high stage valve to the high pressure.
Jim, got it, Jim.
Yeah.
Thank you. Okay.
Is everybody else okay with that? Super duper. Right. Again, from the notes, what we've got is 2 engines. Yeah, and this one is now showing us the additional part of the bleed air valve coming in. Yeah. Again, from there, pressurizing our hydraulic system reservoir. We know why we needed that. Again, pressurizing the water supply. We'll look at water waste, I think, not tomorrow, day after. Up to your main system distribution. Yeah, so from your APU. And sitting on the ground off to your pack valves. So that's the APU side of it. The engine side, we've just been through. We've got the engine. We've got the pre-cooler taking fan air one way, taking engine air, yeah, the other way, or if there's no major demand on the engine, via the high stage valve through the pre-cooler, and we are going to control that air at around about 230 degrees C. 230 is a figure worth noting, and the 255 for the cutout is worth noting as well. Yeah, so please make sure you whack your highlighters through them. Yeah. From there, we said we're going to go to our anti-icing for the wings. This one, pressure transmitter. So pressure transmitter monitoring what's going on in the system, and it will flick on a light in the cockpit and trip the system off if we've got a problem. If there ain't no problems, yeah, then that hot air is going off to the cooling packs that we talked about last week. Nothing else really to mention on there. Everybody okay with that? Because there is something clanging at my head about the APU.
Which order you said to be highlight, Mr. Jim?
The 230 and the 255.
Okay.
Right. I'll maybe come on to it in a couple of minutes in the presentation, but while it's in my mind, while I'm thinking about it, as we go through the various systems, yeah, and we talk about the different components, and it goes through pneumatic ground service connection, portable water pressurization. In there, last page before section 4, there's a thing that says APU bleed valve. It's on page 34 in my book. I'm not sure about yours. Yeah, that APU bleed valve, yeah, fitted downstream of the APU in the air ducting. When the APU is operating above 95% RPM, let's just see if we can see it there. APU bleed valve, yeah, from the APU. If the APU is operating above 95%, that bleed air can be opened to supply air to the system. If the bleed air or the APU is operating below 95%, yeah, we can't supply from the bleed air from the APU. So it's got to be running above 95%. Stick your highlighter through that. Like I say, I'll probably come on to it in a minute in the presentation, but just while it's sticking in my mind, I'd rather let you know. All okay with that?
Yes.
Excellent. Right, you'll see up just past the pressure transmitter, yeah, in the system we've got an air cleaner. We don't want dirty air going in. And the air cleaner is quite a simple device. It's just there to remove dirt and dust from the engine supply. If you think about the engines, the temperatures they're running at, there's going to be dirt, there's going to be carbon, small particles, and we just need to filter those out of the system. And we do that via the air cleaner. Yeah, the air cleaner is just a series of little baffles, yeah. And as the air comes in, yeah, as the air strikes these baffles, inertia will cause any particles to get deflected into a little collecting chamber. The rest of the air will carry on its merry way off into the system. Yeah. Above the cleaner, there's what we call the purge valve. Yeah. So the air comes in, hits these little veins. Yeah. Any particles in there are just going to carry straight on, and those particles will end up in the collecting chamber. Within there, yeah, just above that, we've got a little what we call the purge valve. Yeah, purge valve. Yeah, takes a tapping of pressure. Flicker solenoid. Yeah, so the collector gets full. Yeah, or periodically, automatically, the solenoid will energize, and the solenoid will open that little pipe or pressure line up. That pressure line will then press down on a wee valve, which in turn opens a flap. The act of opening that flap causes a sort of suction, and any crap that's caught up in the collection chamber is sucked out and blown out to atmosphere. Yeah. So out via the I should say via the purge valve. Yeah, the dirty air is just whacked out to atmosphere. So the cleaner is cleaning the air. The purge valve is getting rid of the dirt, the dirty air. Okay with that? Yeah, pneumatically operated, yeah, just a little tapping of pressure for somewhere down the line. As soon as the solenoid opens, that pressure pushes down on the plate, Yeah, that opens up and that dirty air is sucked out to atmosphere. Everybody okay with that? Fantastic. Yeah, your potable water. Yeah. Most of the water that's going to be carried in in fact, all of the water that's carried on the aircraft is what they class as potable water. Potable just means it's fit for human consumption. So even the water that they use for cleaning the toilets, prior to cleaning the toilets, you could take a mouthful of that water and it shouldn't harm you. I am not recommending that you do that. So the water kept in tanks, yeah, and those tanks are stainless steel or fiberglass, some sort of reinforced plastic. Again, we'll look more detail, or the B1.1s and the the B2s will, when we split, because I think the helicopter guys are going off next week to do something different. Yeah, so that those tanks are going to hold the water. That water used in the toilets and the galleys. Yeah, but that water needs a head of pressure behind it to get to where it needs to be. So what we're going to do is just put a small tapping of bleed air on the top, just to give it a head of pressure, so it'll flow through the pipeways to the taps, to the galleys, to the toilets. Yeah, that 10 to 50 psi. In this case, we're going to use bleed air. Some aircraft have a different method, but usually it's going to be the engine air that we're going to use. So that's going to give us our potable water pressurization. Other services, yeah, hydraulic reservoirs. We said we need to pressurize those to make sure that the pumps don't stagnate, to make sure that the oil doesn't cavitate, so we don't get a negative pressure, and it stops the oil from boiling at high altitudes. We can use that bleed air again for our anti-icing, our thermal anti-icing, so we can run hot air down the leading edges of the aerofoils. And pressurizing our fuel tanks. We said the other day when we did fuel, we're going to have the inward and the outward vents, but on the inward side, what we need is a positive pressure on top of the fuel, just to prevent the tank from cavitating, and to make sure that fuel is got a little bit of oomph behind it, just to push it on through the pumps and what have you. But mainly having that positive pressure in the tank is going to prevent any structural faults occurring. Other stuff we can use it for, the windscreen rain repellent. We said when we put rain repellent on the windscreens, yeah, we might use a little bit of bleed air to help it along. And the other thing, when it talks about rain repellent, we talked about blowing bleed air up the front of the windscreen, so rain can't actually impinge on the windscreen. Yeah, so the rain is blown away, diverted before it actually gets the windscreen. We might use it for boundary layer control. Boundary layer control we don't really go into as part of the course in any great depth. But what your boundary layer control is doing, if you think back to your aerodynamics, yeah, the air that's flowing over the aerofoil, we want to keep that attached to the aerofoil for as long as possible. One of the ways we do it is with vortex generators. But one of the methods they used on older aircraft, and it is coming back now as part of design, is to actually blow air across the top of the aerofoil. And by blowing air across the top of the aerofoil, yeah, we're actually encouraging the air that's flowing over there to stay stuck on the aerofoil for longer. So the boundary layer remains attached for a lot longer, and obviously that means more lift, more lift, less drag, all the other good stuff that we talk about. So if you talk about flying surface boundary layer air, that's what it is. It's just blowing air over the top of the aerofoil to keep the boundary layer attached for longer, keep it energized for longer. Indications, controls, yeah, we're back to where we started really. We're going to have a bleed air control panel. Bleed air control panel, yeah, we've got our packs we can open. We've got the main bleed air feed from our bleed air valves, yeah. APU feed from there. We've got our indication of a fault or a failure. We've got our pack valves. We can select the pack valve open or on or off, I should say. We've got our temperature indicator. Remember we talked about duct temperature the other day, and that duct temperature we can monitor. Likewise, we can see what's going on in the cooling packs. Anything else on there that we need to mention? Not really. Not for what we're doing today. But you've got your bleed air switches, opening the bleed air shutoff valve. Isolation valve. Yeah, we can operate the isolation valves from the cockpit or the flight deck. Overheat lights. Yeah, if we've got an overheat, we'll get a warning caption. And there's also going to be a test facility there to test for overheat to make sure that that's working. It's going to pick up. The engine bleed valve, yeah, making sure that that is opening and closing. And again, we've got a test facility there, so we can operate the valve without having the engines running. Pressure gauge, duct pressure, see what's going on there. And the usual warning caution lights that we've already mentioned. We talked about the wing body overheat. That is from the anti-icing. So if the anti-icing is running too hot, we've got the warning light there. The conditioning packs, if they trip off, we've got a warning light. And if the bleed air trips off for any reason, again, the crew need to know about that, so they'll get a warning. Pardon me, a warning light in the cabin. Your ducts, your pipe work, yeah, the ducting for the hot air side of things is normally stainless steel or titanium piping. With that piping, we need to make sure that somebody asked me the other day about bellows. That's an example of the bellows. We need to make sure we give a facility for the pipes to expand and contract. Yeah, because you've got really hot air flowing through them, the pipes are going to expand. If we didn't put in some means of allowing for that expansion, then we'd be creating a potential for real trouble. So we'll put in some sort of expansion valve, be it bellows. Sometimes we'll just leave a gap between the flanges of two mating pipes, and that allows for growth due to heat. Your hot air pipes are normally held together with V-band clamps. The V-band clamps may or may well not have a gasket between the mating faces, a metal gasket. Sometimes they do, sometimes they don't. Just depends. That gasket metal seal. Held in place by brackets, suitable supports. V-band we mentioned, expansion couplings we've mentioned. Can't think of anything else vital there. No, that's pretty much it. Yeah. So the material the pipework's made out, the expansion contraction catered for. Badoom. Hot air. Yeah. And we said that anywhere we're going to run hot air, if we get a leak, there is a potential for an awful lot of structural damage. So what often happens on larger aircraft, they will put overheat detectors running adjacent to the ducting. Those overheat detectors can take various guises. Some of them are little spot detectors. I'll show you those tomorrow when we do the fire. We can use continuous loop firewire, continuous length, I should say, firewire that'll detect an overheat. And a lot of sort of smaller aircrafts adjacent to the hot air ducting, they're using this heat-sensitive tape. So if you get an overheat, the tape will change colour, and the tape is regularly inspected. If we see any change in colour, we know that we've got an overheat in that area. We know we need to carry out specific tasks to alleviate that. And that, guys, was pneumatics. Has anybody got any questions on pneumatics at all? No? Has anybody got any questions on anything that we've covered? No? Right. Well, if you've got no questions and you're happy with everything that we've covered today, I've got nothing else. Yeah, I've got nothing else for the time being. What we'll do tomorrow, we will cover the fire protection side in the morning. If you wish, we can have a run over all the systems that we've covered. We can have a recap of those tomorrow afternoon, or if you prefer, if the helicopter guys are happy, we can start on the B1.1 B2 section of the notes.
For helicopter,
how many helicopters, guys, have we got?
me 1, Vikas
Krishna?
2, Naveen.
Raise hand, please. Who are the helicopter guys?
Yeah, if you're helicopters, stick your
Maybe
mix.
6 people.
2, 3, 4, 5.
And Santosh Bashal also. Maybe
So
6.
6 of you.
Yeah.
Right. On Wednesday, we were meant to split. Yeah. The program, wherever the program's gone. Yeah, the program that I've got. Yeah, we're going to do the systems up to the 19th. That's the B1.1s, the 1.3s, and the B2s. Yeah, that is tomorrow. And all I've got to finish off tomorrow is fire protection. So tomorrow I'm giving the 1.3s the option. Tomorrow afternoon we can either run through all the systems again and cover anything that you're not happy with, or I can carry on with the B1.1s and the B2s, and you guys have got that afternoon to carry on your revision. Yeah. So have a think about it. See how you feel. If you want to to finish at lunchtime tomorrow, you can. If you want me to go over all the systems again, just to make sure that we've covered everything that you want, I can do that. As far as the B1.1s and the B2s go, yeah, from Wednesday, yeah, it's just we're losing the B1.3s. So right up till the 27th, we're going to do the common systems that the B2s and the B1.1s need to know about. 4th to the 16th of February is when you come back together. The B1.3s join in, the helicopter guys join in, and that's when you're going to do your electrics and avionics and all that complicated stuff. And then the helicopter guys will carry on and do the helicopter side of things. That's all I'm.
Hello, Jim.
Yeah.
Regarding this, all our class after tomorrow or after 2-3 days, if you have any confusion, we can message you or anything we can do. In the
yes.
Okay,
Yeah.
we'll text you if any issue on this concern.
If there's what, sorry?
In this issue which we have learned from your side, if any problem created, then we'll message you or we want to contact you. Give your address or message for my messaging purpose. Because in the middle of the class we cannot disturb you, or at night we cannot call you, so that if anything, any problem occurs, then we will message you. It will be better or anything from your side.
Yeah, let me have a think about that one. The best way to do it.
Okay.
Yeah, because if I've got 6 people sending me individual messages with individual problems, I'm not going to have a chance to sort out the other classes as well. So we'll have to maybe I'll set an afternoon aside for everybody. Yeah, that's the B1s, B1.3s, the B2s. We'll set an afternoon aside later on. So if anybody's got any questions, we can do them all together, all as a oneer.
That is the best idea. Thank you.
Well, again, if you guys are happy enough doing that, if you can all get to a computer, I'll tell you what. Shall we say? I'll confirm
Jim,
it tomorrow, but maybe Friday afternoon or Saturday afternoon.
Sorry, Jim. Northern, we have one Viber group. Then we will join you in that group and we will message you if any problem. Okay, that will be better.
Yeah, right at the end.
Okay.
Yeah, that's. Where's that gone? Yeah. Yeah. So we'll do that tomorrow. Again, if you helicopter guys, if you want me to go over anything tomorrow afternoon, yeah, because fire protection will only take a morning. It's very, very easy. So the 1.3s, I've got the option then at lunchtime of either asking me any questions or banging out and leaving it till. What I'll do, because that'll give the B2 guys a chance as well. Yeah. We'll say that Wednesday afternoon, the 27th, or the morning of the 28th. 28th, 29th. Right. That would be the best day to do it on the 3rd of February. Yeah. What we'll do, we'll have a big recap of everything. Yeah, so that's the B1.1s. They can go over everything that they've done. The B2s, likewise, because they're not doing the section at the end there. That's just the B1s. So it'll give the helicopter guys a chance. It'll give the B2s a chance, and it'll also give the B1s a chance. So right at the end, that 3rd of February, we'll make that a recap day, a recap for everything. Does that sound good?
Okay, sir. No problem. Can do it.
Now, well, have a think about it. If anybody's got any problems, let me know. But that way, everybody gets a fair crack of the whip. Everybody gets a chance to ask their questions. And everybody gets the benefit of a recap and a go over. If you've got any really pressing problems in the meantime, something urgent, yeah, then you can message me. Or email me.
Okay, Jim.
Yeah.
We'll
Have you got
do
my
it.
email address? Yadav's got my email address, so he can send that on to you. But it is only for really urgent things, not niff-naff, not because you've not read the notes properly. It's got to be a real problem, okay?
Okay, sir. We'll do it.
Okay, Jim. Yeah. Have a good day.
Okay, has anybody got any questions, anything else they want, or do you want to call it a day there? I'll stay online for a little while if anybody's got any problems, any questions, any queries. Failing that, I will see you all tomorrow for fire protection. Okay?
Okay, sir.
All right, have a pleasant evening. Take
Thank
care.
you.
Have a good day, sir.
Jim,
Yeah.
one very last question. What about maintenance, pneumatic system maintenance? We do not require it?
Not really. It's just common sense stuff. All you're going to do is carry out your maintenance in accordance with the manual, aren't you?
Mm-hmm.
Well, that is one thing. Is everybody still there? One thing I did forget to mention.
Yes, yeah,
Pneumatic system identification. Yeah, the white background with the black continuous cross. Yeah, that identifies your pneumatic ducts. Not that I've seen a question on it, but the rest of it, no, everything's okay there. No, just following the maintenance manual for that. Leak detection we've talked about, fire detection. We'll look at spot detectors tomorrow. No, that's fine.
Jim, what about this damage, this quarter range and this causes permissible if they are not more than 10% of duct wall thickness and providing the bottom of scratches. This, following this duct, up to which tolerance we can say this is serviceable or this is unserviceable. These are important or not?
No.
Okay.
No.
Then okay, Jim. Then good night.
Yeah, okay. I can't see anything else there. I'll have a look through, and if I do see anything, I'll let you all know tomorrow.
Okay.